Welcome everyone to the Ventilation Symposium, the NAPHN Ventilation Symposium. It's great to have you here today. My name is Ken Levinson, and I'm the Executive Director of NAPHN. NAPHN, as you may know, is a national nonprofit network with regional chapters and members from coast to coast. NAPHN is affiliated with the Passive House Institute and the International Passive House Association, part of a global network of peer-to-peer knowledge sharing. And we're focused on Passive House education because Passive House education is really what drives market transformation. As many people remark, once you've gotten a Passive House education, you simply can't look at buildings the same way again. So we'd like to thank our partners, sponsors, and supporters who help make all our work possible, including the symposium. We couldn't do it without them. So let's turn to the event at hand, our ventilation symposium. We have been thinking about it for some time now, and we're really happy the day has arrived. The fact remains, that in designing and building high-performance buildings, building ventilation is often an underappreciated component. The pandemic has made the health implications of good ventilation more obvious, but the energy impacts remain largely obscured to the public. Yet when we target radical whole building energy efficiency, like we do with Passive House, ventilation energy impacts become significant and hopefully obvious. As carbon emissions goals tighten, efficiency demands grow, Passive House performance levels should be normalized. And we think this offers an enormous opportunity. This focus on building ventilation performance is an opportunity for the ventilation industry around the world and in the US. If component testing outputs can provide Passive House modeling data inputs and products can meet Passive House targets, there's an emerging high-performance global market that can be served to the benefit of everyone. So if I can say, the goal here today is to speak really to the fundamentals of Passive House ventilation, the first principles, and build a common vocabulary and hopefully an understanding of what the strategies are and why. We'll do this in presentations and moderated discussions, including questions from you all in the audience. Please state your questions in the chat. Some may be answered there within the chat, and some may be introduced into moderated discussion, and possibly both. So I would like to briefly introduce the speakers because they're the ones that are going to help demystify these different issues, probe, question, discuss. And so I'm honored to briefly introduce the speakers for both sessions right now. And I should note there are extended versions of their bios on the event webpage. So in alphabetical order, Lois Arena is the Director of Passive House Services at Stephen Winter Associates. Lois possesses over 25 years of experience in the building science field and has extensive experience with new and existing buildings. Lois holds both U.S. and international Passive House consultant certifications and is currently consulting on some of the largest and most difficult Passive House projects in the world. Enrico Bonellari is a co-founder of EMU Systems and holds 2 master's degrees, one in architecture from the University of Parma, Italy, and one in design science from the University of Sydney, Australia. As a registered Italian architect and certified Passive House designer, he has worked in Australia, Europe, and North America. Ongoing research in field building science includes data collection in occupied buildings, both Passive House and not, with the intention to investigate the relationship between occupancy, climate, building air tightness, and ventilation. Matthew Friedlander has been active in the energy recovery ventilation field since joining the original founders of Renew Air in 1993. Matthew has been Renew Air's member representative to the Home Ventilating Institute and the Air Conditioning, Heating, and Refrigeration Institute since the late 1990s. Among numerous other work in testing and standards development, he was most recently the project manager for the development of ISO 21773 methods of test and characterization of performance for energy recovery components to be published shortly. Dr. Bertold Kaufmann, since 2000, conducts research at the Passive House Institute on the thermal properties of buildings and its components. especially design of windows and ventilation systems, and combined systems with heat pump and air conditioning, heating, cooling, dehumidification, and domestic hot water preparation. He advises architects, engineers, and construction contractors on passive house design for new build and retrofits. Much of the scientific work and the institutes has been published on passipedia.org to provide wider access to reliable data on temperature, energy consumption, thermal flows, and more for energy efficient design of buildings. Mike Moore is a consulting engineer at Stater LLC with over 15 years of experience in technology transfer and demonstration, building and energy codes and standards, product development, and R&D of energy efficient and durable buildings and systems. With respect to ventilation codes and standards, he drafted the whole house mechanical ventilation requirements of the IRC. He serves as the vice chair of ASHRAE 62.2 and works as a consultant for manufacturers in the industry. Andrew Peel is the founder of Peel Passive House Consulting, and his primary areas of expertise are in low carbon buildings and renewable energy. His professional and academic experience ranges from consultancy, program management, authoring technical and non-technical articles, course and lecture delivery, technical research. Andrew provides passive house and sustainability consultancy, certification, and training services to the building sector. Dr. Rainer Pfluger is an associate professor at the University of Innsbruck, Unit of Energy Efficient Buildings since 2008. From 1999 to 2008, Dr. Pfluger was a scientific assistant and project researcher at the Passive House Institute, working on the development of standards for ventilation, windows, and other aspects of high-performance building. Charles Stevens is a consulting systems engineer. As a senior codes and standards engineer at the Northwest Energy Efficiency Alliance, NEEA, Charlie designed and managed NEEA's pilot project to demonstrate very high efficiency HVAC systems for new and existing commercial buildings as a systems solution. In addition to active consulting, Charlie is co-chair of the Canadian Standards Association Test and Rating Procedures Development Committees, working on new load-based procedures for heat pumps and air conditioners, air-to-water heat pumps, and commercial H and ERVs. Josephine Zarica is a principal at Dagger Engineering and has extensive experience in project management, mechanical engineering, and sustainable design. She serves as the vice chair of the ACEC New York Metro Region Executive Committee and the Energy Code Committee. As one of Dagger's Engineering's primary sustainable design specialist, Josephine is well-versed in energy conservation strategies that promote efficiency while meeting budgetary requirements, including passive house design. So with that, welcome speakers, welcome audience. One final quick note before we start. I want to give a heads up that when we finish this first session, when it ends for the 15-minute break, there will be a survey that appears on the screen. We hope you take a few minutes to fill it out. It will be really helpful if you could answer all the questions that you can. It's about 26 questions long. So with that, let's get started with session one and Rainer Pfluger.
Yeah, hello, and thank you very much for this kind introduction. I'll share my screen now. 1 second, please. So you should see the screen now. Does it work?
Yep.
Okay. Yeah. So welcome from my side, and thank you for the invitation to this ventilation symposium. Yeah, nice to meet you all virtually, and yeah, thank you for the introduction. As you already told, I am in the ventilation business since around 20 years now, and I will present you today the high efficiency, high performance ventilation on issues like how to test, how to design them, how to install, and why do we need quality assurance? What is the key role of quality assurance? So what I'm doing here at University of Innsbruck is research, teaching, and testing in terms of ventilation also. So all things of energy efficient buildings, but ventilation is really a focus point in our work here. And this is not only for new buildings, but also for refurbishing, so for existing buildings. So ventilation has a really long history. So 30 years history of high efficient ventilation is also the 30 years of history of the passive house. On this slide, you see the first passive house in Darmstadt-Kranichstein. On the left side, the photo, and on the right side, a cross section of this more or less prototype building in those times. A lot of the building products were not available in this time. So year of construction, 1990. So it was scientific prototyping. It was monitored intensively many years. Up to now, there's still some monitoring inside. And you know, Wolfgang Feist himself is living in one of these flats of this row house, of this terraced house. And yeah, first there was some simulation work. It should work theoretically, and then it was built, and just to see if it works in reality. And one of the key elements of this building, as you know, the passive house building, is the ventilation system with high efficient counterflow heat recovery. So it was well known in those times that it should be necessary to have a high efficient counterflow ventilation, but it was almost not available on the market in those early times. So you see in the cross section, the ductwork, you see the core of the system, which is installed at the ceiling of the cellar, and it's a counterflow heat exchanger. Yeah. But as already mentioned, it was not easy to buy it from the shelf. So high efficiency means counterflow, means a large area, a large surface area, which is necessary. And then you can achieve heat recovery rates in the range of 70 up to 95%. Yeah. So you need either a long or some parallel 2 or 3 units in parallel with a little bit shorter, but still counterflow heat exchanger. That was already well known in those times, but it was mostly not available. Only this type, you know, the cross-flow heat exchangers, which are not suitable for passive house buildings because the heat recovery rate is only in the range of 40 up to 60%. So this is not suitable, okay? But where to buy if it's not available? In those times in Germany, it was not easy to become a product of this type. So it was bought in Sweden, and then it was self-made enhancements necessary to achieve the heat recovery rate of at least 80%, which was a really good value in those times. Nowadays it's much better. But yeah, this was the goal, to reach this value. And this Swedish type, you see it on the photo on the right-hand side, is a Temovex, which is a really long and big box and has a heat recovery rate of 80% from the product data, which was written there. Yeah, it was a counterflow, okay, yeah. To build a high efficient unit out of it, it was not so easy because the fans were in those times AC fans with a power consumption of around 100 watts, much too high for an efficient unit. So the fans were changed to a DC fan with electronically commuted motors with only 25 watts. So really high efficient and high and very good controllable with electronic control. it was not available, so they built their own electronics. You can see this old photo below here, and this is the DC fan. Yeah, and then the enhancement went on because the insulation of this unit was too bad. So they added an additional polyurethane insulation around the box. And they had to enhance the airtightness. The leakage rate was too high. And after this enhancement of the airtightness, the leakage was smaller than 1%. That's even today a really good value. And so they learned a lot about how to produce a better unit, but it was not available ready from the shelf on the market in those times. And then they installed the unit and started it and wanted to test it and measured the heat recovery rate and were really disappointed. It was rather low. I don't know exactly how low. It was in the range of less than 70%. So it was disappointing. And the question was, what is the reason? We did all we could think about, a good heat exchanger. The casing was re-insulated, but the performance was bad. So what was the reason? Well, the flow distribution amongst the plates, the heat exchanger plates, was very bad. So they installed flow distribution system made of a perforated sheet. And after this enhancement, well, then finally they reached the 80%. So long story, in those times, it was not easy just to plug and play like it's today. That was 30 years ago. And yeah, that's a photo of this old unit and the box, which was insulated with few foam plates. And on this left-hand side, you see the infrared picture, which is in this mostly bluish color, so 50 degrees centigrade, which means it's perfectly cold outside. The insulation works well. Just to remind you, the system is in the cold cellar outside the insulated envelope of the building. Yeah, and then it was measured again, and you found a heat recovery rate of 80%, which was really good for this first prototype, mostly handmade and things like that. So the total heat recovery area was 2 times 90 square meter. That's a really large system. Yeah, that's the history. But what's the reason? Why all this effort and enhancement? Why do we need high efficient ventilation? Well, the first thing is comfort. The reason for ventilation is health, good indoor air quality. And the reason for high efficiency, the first and most important, is very simple. It's comfort. You have preheating of the air, so it's supply air temperature, which is above 30.5 degrees centigrade. And with this enhanced temperature, you avoid any draft risk when you blow in the air in the dwelling. So comfort, comfort, and comfort. That's also for your customers the most important reasoning for high efficient ventilation. And then, the climate change. We have to make climate protection. So we have to save ventilation losses, reduce electricity consumption. So save energy, save our planet by reduction of CO2, of primary energy. And this is done by heat recovery, which is a high efficient heat recovery, and with reduction of the electricity by high efficient fans, what we have seen already on this historic photo. Yeah, and then the economy is sure the energy, the heat demand for ventilation, heat losses is a very big reason. And you have to reduce the electricity consumption, so you save money for electricity. It's running 24 hours a day, so even with a low power consumption of some 25 watts or whatever, it's some electricity consumption, and keep it as low as possible. Well, and the high efficiency is necessary to build a passive house. You will see if you calculate for the energy balance, and you do it, if you are a planner, you do it on your everyday business. Yeah, it's not so easy to keep the threshold, and you need a high efficient ventilation unit to keep the total energy balance within the boundary limits and have economic passive house. Well, with a less efficiency ventilation system, you have to compensate for. You can compensate with better insulation, better windows, and so on, but you have to compensate it with extra money, extra effort. So it's a good advice to have high efficient ventilation to keep the balance in that right way. Yeah, though after installing the first prototype in the first passive house in Darmstadt-Kranichstein, it was sure that the units on the market needed some enhancement. A lot of research and development should be ongoing. So it was rather important, and it's still today, to have a lot of consultancy for the ventilation industry, for the manufacturers, for the industry, and for the installers and so on their way to high performance ventilation systems. And for sure, PHI raised the awareness for the importance of these high efficient ventilation systems. So 30 years ago, there were these cross-flow heat exchangers, these low efficient fans, and nobody cared about it. There was no awareness about, well, a little bit more energy for driving the fans, some less efficiency for heat recovery. Who cares? So, but then when the passive house development started, it becomes immediately obvious that we need high efficiency ventilation. Though, and really, I think that was awareness rising of PHI and their certification work and quality assurance. Yeah, that we have such a lot of high quality systems and products on the market nowadays. It needed a lot of lab testing and certification work and quality assurance on site to come to this status on the building sites and on the industry, what we have nowadays. It needed consultancy for the development of the departments of manufacturers and for the industry. There's always some possibilities for enhancement, even for the units of today, and there is still no end of improvement. We do still a lot of research in high efficiency ventilation in University of Innsbruck, for example, or in other universities and departments, development departments of industry. It's still ongoing, and there's a lot of new findings, and it's still improving. So consultancy is still important, not only for manufacturers, but also for the planning. Yeah. Planning of buildings, but planning for ventilation systems and for the installation. Yeah? And then quality assurance on site is also rather important. And this holds for big units, central units, or smaller units, unit by dwelling or unit room-wise. It's always important. The whole chain of consultancy and quality assurance is important for high efficient systems. So what's going on 30 years later? That's a really success story, which is from 1990 to 2021 nowadays. So at the moment, I just looked yesterday on the homepage how many certified systems are available in the range of 600 cubic meters per hour. It's 239 units certified, available on the Passive House homepage. You can see all the certificates, and at least 84 units in the bigger units, which are in the range of larger flow rates than 600 cubic meters per hour. So really success story. You see some photos below, but there are really a wide range from smaller systems of central systems, and for different applications. Just to give you some examples, here a flat unit which you can install on the ceiling, or these box type units, and units in combination with other systems like heat pumps. These are the passive house compact units. These are extra number of certified units that are not included in these numbers. Yeah, what are the best heat recovery rates at the moment on this list of certified units? It's 93% heat recovery rate. Really good electric efficiency, low specific electric power, and yeah, all of them have counterflow heat exchangers. There are no cross flow anymore. I think most manufacturers changed their manufacturing process, and cross flow is more or less yeah, out of the market, out of the game of efficiency ventilation. So what are we doing in University of Innsbruck? We do lab tests. We have climate chambers in our cellar and test units. So what kind of units? Ventilation units, but also these passive house compact units, which are a combination of heat recovery ventilation plus domestic hot water plus heating. So very compact unit, as the name says already, passive house compact units. You see on this photo on the right-hand side here below, this is some of these compact units, which are really small, so 70 centimeters by 70 centimeters floor print, and 2 meters so approximately high. Yeah, and they do all what you need in a passive house, the complete ventilation, heat recovery, and domestic hot water and heating for the passive house. Yeah. That's the reason why we need a lot of auxiliary systems in our lab, because we need some heat source and sink, and we need a really accurate measurement system for the flow rates, for the temperatures, for the humidity, because we not only test HRV but also ERV systems, and especially therefore the accuracy has to be high. We have so humidifier, steam humidifiers in our lab, and all the calibration work for the sensors and so on. Yeah, that's our test unit, and we use it for tests and consultancy for manufacturers. If they want to enhance their systems, we can help them via optimization, changes, and simulation work, yeah, to enhance the systems. Yeah, so quality assurance for high efficient ventilation. First, we will see how to test the heat recovery rate. What are the important issues there? First of all, the energy balance on the exhaust air side. We have to test under flow balance conditions. We will see later on why. And yeah, we have to have a look on the leakage rate. It is also to be tested. It has to be tested on the internal as well as the external leakages. And then last but not least, the fan efficiency have to be measured. Well, that's the simplest task. It's quite an efficiency, electric efficiency measurement. Yeah, what I also want to mention just in brief, it's the HRV versus ERV, and the role of humidity recovery also in the building, but also in terms of the energy balance in the building. I put it into quotation marks here. That's ERV because I don't like the term of energy recovery, because in fact it's almost no effect on energy recovery. It's a humidity recovery. I like this term more. Well, and then quality assurance of planning and installation. That's for you as planners, architects, and so on, installers. Very important to avoid long ductworks. Yeah, that's really important. You have to reduce the pressure drop And you should use at the very best an automatic flow balance control, or you do it manually, but then you have to be really regular in maintenance and to recontrol the flow balance if it's still working good. Why? Because if the flow balance is incorrect, you will reduce the efficiency and reduce the heat recovery rate. And then, last but not least, the sound protection. You need silences and structure-borne sound decoupling. I will also come to this really important point. Yeah, but for you as planners, these first two issues, the avoiding of long ductwork is important, and the reduction of the pressure drop is important. And you as planners have a lot of influence on this, and then you save a lot of energy and electricity doing this. And you reduce the cost for installation and maintenance as well. So the first and most important issue, how to measure the heat recovery rate according to the energy balance. And that's pure physics. That has nothing to do with standards or whatever. It's only the physics behind that you want to make an energy balance. And as planners, you know, normally you do the energy balance boundary at the outer surface of the building. I marked this in red. This red line is the outer surface of the building. And then it's clear how to make an energy balance. You balance all the incoming and outgoing energy flows, which is the enthalpy flows from the air ducts, as well as, in this case, the electricity which is coming in from the grid, from outside, to feed the fans with electricity for driving the flow. The energy balance boundary, you have the transmission losses and the energy gains through the windows and the internal gains and so on. This is all you do with your energy balance calculation. Most of you do it with the PHPP, the planning passive house planning package, which is nothing else than an energy balance calculation. And it also uses exactly this balance boundary, and it calculates with a heat recovery system. And now we have to calculate the heat recovery rate according to this energy balance. Now we only focus on the system itself, on the ventilation system and the ventilation losses, which is written here. This is the energy flow of the ventilation losses. What's outgoing? It's the enthalpy flow of the air, exhaust air and outer air, and you can subtract the electric power for the unit. By the way, it's the total electric power of the system. It's the consumption of both fans, plus the control unit, plus some auxiliary, whatever is needed for the running the system. That's the electric power which is on this side. So you have this equation, and now you just have to solve the equation by the heat recovery rate, which is this formula pointed out here. Very simple. You get out the heat recovery rate, which is just this way done by certification of the passive house components, all listed in the certified component list. And how to test and how to measure it? You have to measure the temperature of the outgoing air, which is the exhaust air passing this energy balance boundary at this place where this small red circle is. And what is incoming is the outdoor air. You measure the temperature of the outdoor air, and you know the temperature of the extract air, which is the indoor air in the building. That's the whatever 20 degrees centigrade in the building. Yeah, and then you can measure and calculate the energy balance. And that's just the same way we do it on our test lab unit. That's just the way we do the rating for the performance test. It's written in the test criteria for passive house ventilation units, and there are some more criterion besides these heat recovery rate. It's also the hygiene criterion. It is all about the filters. The outer air filters should be fine filters, and the extract air filters should be at least G4 coarse filters. And the test is done with these type of filters installed. That's important because fine filters have higher pressure drop than coarse filters, and it's not a fair test if you test with core filters and then you have lower electricity consumption. Though that's why it's done with these filters installed, and it's important, this hygiene criterion. Yeah, what are the comfort criterion? That was the first issue I mentioned in my presentation. You shouldn't blow in air with lower temperatures than 60.4 degrees centigrade at outer air temperature of -10 degrees. You should have at least a control possibility of 3 airflow levels, so 70, 100, and 130%. And then the noise protection is a really important issue about acceptance of these units in the building. You should be lower than 35 decibel in the service room and 25 decibel in living spaces. Therefore, you need some silences, and this is also part of the certification criteria. And then, last but not least, as mentioned, the efficiency criterion and the criteria. And the most important is the heat recovery rate, threshold level at limit value of 75%. Well, most of them have higher values now, though in the range of 80, 85, or even higher than 90%. Yeah, but 75% is the limit value. Same for electricity efficiency. You need to be better than 0.45 watt hours per cubic meter, and the standby shouldn't be higher than 1 watt. That was a KO criterion in the first year, so not a lot of manufacturers did reach these low standby values. So it's not so easy to have only 1 watt. If it was not possible, they should have at least a switch for disconnecting from the grid, because then you have 0 watt standby consumption. Yeah, but from nowadays electronics, it's not a big deal to be lower than 1 watt for the control. Yeah, and then good air tightness is important, so less than 3% leakage rate. And which is very important, is the criterion E, the balance of outer air and exhaust air. And this is also tested in lab conditions, and the unit is adjusted to flow balance to do the testing. I'll come to this point later on. Yeah, and then last but not least, part of the test is the frost protection at -10 degrees centigrade. Yeah, how to measure the efficiency? It's all about measuring the exhaust air temperature, as I already mentioned, the outer temperature, measuring the electric consumption of both fans plus control. And yeah, that's how to do it. And then you put all these values in the formula. Why do we have to measure under perfect flow balance? So exhaust air equals outer air flow. Just make a experiment. What will happen if we have excess outer air? So here the flow rate of the outer air is higher than the exhaust air flow rate. What will happen? I just draw you the building to clarify what will happen. Quite easy. The excess flow will leave the building through leakages. These are these blow arrows you see all around here. What will happen? You have some overpressure in the building, and the difference between this flow rate and this flow rate will leave the building. To be precise, it's not the air flow rate, but the mass flow rate, not the volume flow, but the mass flow. Yeah. So the balance is equal via the leakage rate. Yeah. But what will happen with the temperatures? This temperature would rise. So at best, the best efficiency you will have under equal flow conditions, and this is the test conditions. Don't measure at unequal flow rates. That's the issue. Then you should limit the leakage rate to values lower than 3%. Why? Well, the reason behind it is clear. It's a matter of comfort, and you should avoid odor transmission. If you have some leakage from extract air to supply air, you could smell it. It always depends on the position of the fans, at which side they are. There is no odor transmission in case of exhaust air and outer air fan situation. But if you have under pressure at extract air, then you can have odor transmission. Yeah? If clever manufacturers would drill a hole between the outer air and the exhaust air at this point where I drawn this blue arrow, then you could cheat and have lower exhaust air temperatures, and then you would have a higher rating. And but this is avoided also by limiting the leakage rates down to less than 3%. Yeah, and then how about the specific electric power? Again, I want to mention it's including both fans. It's not only the supply air fan or the extract air fan. It's both fans plus the power supply plus the control. So the complete sum of the electricity consumption divided by the flow rate, supply flow rate, or it's equal to the extract or exhaust flow rate. That's the specific electric power as it is rated for the certification. Yeah, and this should be as efficient as possible. So please reduce the total electricity consumption, which is both the fan consumption, but also control structures and so on. The standby consumption we already mentioned. It should be lower than 1 watt. And this is also running if the unit is out of operation. So also maybe in summertime when you switch it off, it still has some standby consumption. So keep it as low as possible. And if the unit is running, it should be with this limit value of 0.45 watt hours per cubic meter. How about humidity recovery? So within the last 10 years, they become more and more on the market. And it's really a good idea, at least in cold regions, like here, as we live here in Austria, in the Alpine region. It's rather cold in wintertime, and we have problems with dry air. So it's a good idea to use moisture recovery. And it can be done by these membrane heat exchangers with humidity recovery, with moisture recovery. The drawback is that those units up to now have a little bit lower heat recovery rate, but they have this additional effect of humidity recovery, and they have a really positive effect that they don't need any frost protection in moderate climate. So standard heat exchangers need some electric preheating. These humidity recovery don't need. So that's a really big advantage. And the moisture recovery can reach values up to 60% or even higher. But if it's higher, then you can run into problems with too high humidity. So ventilation is installed to have some dehumidification. And if the humidity recovery is too high, you need some humidity-based airflow control to avoid problems in concern with too high moisture. Here on the right-hand side, you see how it works in principle. It's a membrane like, this Gore-Tex membrane of clothes. It's a vapor transmission through the membrane. If you have some humidity recovery, you can make a water mass balance. And I want to demonstrate it with this graph. It's rather simple. You have outer air coming in with a low humidity rate, and you add some additional water from any water source in the building, which is irrigating of plants or showering or cooking or whatever. So that's this big arrow, which is a surplus of humidity, and the sum of both is leaving the building. That's the standard way if you have no humidity recovery. In winter times, you end up with low humidity rates with relative humidity of around 30% indoor air humidity. If you want to enhance it to have a higher value, it's a good idea to use a humidity recovery. The water mass balance looks quite the same, with the exception of what happens indoors. The part of the humidity is somehow recirculated. It's taken out of the extract air and added to the supply air, and then you end up with a higher humidity level. But the mass balance is quite the same. All the water you put into the building will leave the building on the long run. So the balance is clear. So there is almost no energy saving. So I don't like this term ERV, because it's not an energy recovery. It's a humidity recovery. So you have some savings, some energy savings also. It's rather small. With this formula, you have a surplus of 0.08 multiplied by the humidity recovery rate. And this surplus is even limited, according to the PHI certificate, to a value of 4.8% in case of higher humidity rates, higher than 60%. You will say, okay, but there is some energy effect if you have ERV instead of HRV. Well, you are right. There is energy effect or energy saving, which is according to the reduction of energy for humidification. If you want to have some stabilized humidity ratio, for example, 40% constant throughout the winter period, you need a lot of energy by steam humidification or whatever, and you can reduce this energy demand using an ERV. Okay, then you reach the same level of humidity with a lower energy input, Okay, you have this effect, but if you don't use humidification, the effect is rather low, and it's like this. So that's why there is no add-on to the energy efficiency, heat recovery efficiency, but only a very, very limited surplus. Okay, now we come to the quality assurance of planning and installation. First thing I want to mention is please avoid long ductworks. Yeah? It can be done by cascade ventilation, for example, yeah, the right placement we will hear in another presentation in today's ventilation symposium, how to avoid long ductworks. It will be an interesting case study what will be shown. And then reduce pressure drop. So large duct cross-sectioned areas are good to reduce electricity consumption. And please place the unit close to the thermal envelope, as close as possible. You reduce ductwork, but you reduce also thermal losses, transmission losses through the envelope of the ducts. Insulate the ductwork where necessary. For example, the cold ductwork within the warm building envelope. And please don't forget the soundproofing. Install proper silencers and avoid any structure-borne sound transmission. Please use sound decoupling. I'll show you some examples how to do. So, and yeah, this is obvious. If you install the unit within the thermal envelope, part of the unit and the ductwork is cold and the other part is warm. Supply and extract air is warm. Ductwork, you don't have to care about it. It's within the warm envelope, it's warm, but these parts are crucial. These are the cold parts, which are exhaust air and outer air ducts, and they have to be very well insulated, and they have to be Weber tight to avoid any condensation risk. This is a very old photo of installed unit with really thick insulated ductwork. You see here, and it's with this metallic covering to avoid any vapor transmission and to avoid any condensation. You do it just the other way around. If you place the unit outside the thermal envelope, it's on this graph where you can see the extract air and supply air. Ducts have to be well insulated, otherwise you lose a lot of energy via transmission of these warm ducts in the cold environment. The first Passivhaus in Darmstadt-Kranichstein was installed like this. It was outside the thermal envelope, in this case in the cellar, in the basement. So it was cold and the ductwork were insulated. The supply and the extract air ducts were insulated. But normally you install this unit inside the building, so these ductworks should be well insulated and with a vapor barrier that's required. How does it look like? You see it on this photo. It's a vapor-tight insulation foam material. It has to be well connected to the unit without any gaps. Otherwise, you have some vapor transmission and condensation risks. The ducts should all be connected airtight by each other, but also connected to the airtight layer of the building. It's perfectly done here in this photo. And what you see also on the photo is the silencers. So you reduce the sound transmission through the ducts. How about the filters? We need fine filters, as you know, and they should be as large as possible to have a small pressure drop. It should be at least less than 50 Pascal. You see a good example here. It's an insulated box, and it's these high-grade filters with a large filter surface. Please ensure a regular filter change. Please ensure a well-insulated filter box, which should be vapor tight if it's installed inside the building envelope. And here you see also a fine particulate air filter, which helps for health reasons, but it also helps to keep the unit clean. Otherwise, you have to clean the ducts in the units regularly, and this it costs a lot more than just changing the filters. It's a good advice to regularly change the filters. How about frost protection? You see the graph here. As you all know, in counterflow heat exchangers, high efficiency heat exchangers, you get condensation on the cold side at the extract air side. And if it becomes even colder, then it starts to freeze and you get some frost. To protect these units against frost, you need some preheating as drawn here. You rise the temperature at the outer side, and by this way you melt the ice and frost on the cold side. And you stabilize the supply air temperature. But please be aware of limiting the set point of the preheating unit. That's really a part for you for the quality assurance control. If it's not larger than at least -3 degrees centigrade, a lot of manufacturers do default temperature, which is much higher, which, yeah, it's on the safe side for preventing the frost, but it's not on the good side for energy efficiency. Each degree centigrade higher of the set point needs a lot of electricity if it's electric preheater, or a lot of energy if it's some other preheater. Please be aware of the set point. What's not suitable for passive house units is defrosting via switching off the supply air fan. Why is it not suitable? Because then you have a disbalanced ventilation, and yeah, you don't have the comfort which is suitable for passive houses. Yeah. What you can use is air subsole preheating. You can use brine subsole heaters, or for small units, in moderate climates, electric outdoor heating, or hydraulic outdoor air heating coils, whatever. Or you can skip it completely, as just mentioned in this ventilation presentation. You can use humidity recovery. So then you don't need this frost protection, because the vapor is transmitted through these membranes. Silencers are a critical part. Be aware of it. You need crosstalk silencers and a device silencer, to minimize the crosstalk effect between the rooms, and to minimize the sound from the fans and the flow noise. You know how they look like. On these photos, you see these banded type silencers. That's a really good idea, because you save bendings, and you have even better sound protection if they are bended. This is a flat type silencer. That's good if you have it behind the suspended ceiling and you don't want to lose too much room height. And then how about the solid-borne sound insulation? As you know, the unit is vibrating, and via solid-borne sound transmission effects, it could be transmitted to the ductwork, to the building structure. And to avoid this, you need solid-borne sound insulation of the casing to the ground, and you need a canvas connection to the ducts. As you see here, these are the canvas connections. Also part of quality assurance, please ensure that the condensate of the drainage can run out. Control the inclination of the condensate drain pipe, and regularly control or clean it if there's some dirt or whatever. That's part of the quality assurance. High efficient quality ventilation and how to achieve, all in a nutshell. First of all, you need a high efficient heat exchanger, high efficient fans, as we mentioned. It should be quality assurance on this by testing, by the manufacturer, by test institutes. You need well-insulated and airtight casings. That's, for sure, a really big prerequisite. And energy-efficient control, energy-efficient control for the fans, but also for the frost protection. Again, ensure the frost protection temperature limit. And then the lab testing according to BHI specifications. Ensure that you can directly take the values coming out from lab test to the energy balance, for example, for the PHPP planning package. Then it's really directly compatible for this type of calculations. Yeah, but that's not all. The unit comes from the manufacturer, but you as planners have to do quality assurance of the planning and on the on-site of the installation, and you have to have on-site inspection. Regularly maintenance is crucial, change of filters, control of condensate drain, and so on. And then you really have high efficient ventilation, comfortable ventilation, and your customers will be really happy. And that's all in a nutshell, and I'm looking forward for your questions and for a good discussion. Thank you very much for your attention.
Yes, Matthew.
Rainer, very interesting. Thank you for that. I noted on your slide 18, I believe, there was a way to calculate the energy value of recovered humidity, I believe. And I'm very interested in that. Would you be able to speak to that in a little more detail?
Well, the humidity recovery is rated by the relation between the absolute humidity measured on the lab test. And that's the value the manufacturer can give to the customers. That's interesting. And it's useful to have a high humidity recovery for health reasons, as mentioned. And it's somehow some enhancement also for the energy, but rather limited, as I mentioned. And then you have this formula for calculating the surplus of the heat recovery, which is in this small range of, as I said, 0.08 multiplied by the humidity recovery rate. That's
thank you. It's that formula that I'm interested in. Can you give us some idea of the derivation or background of that formula?
Mm-hmm. Yeah, the background is that the primary effect of humidity recovery is just to rise the level of indoor air humidity. So as I mentioned, from 30% up to 35 or whatever. But there is some additional energy effect also, because you have some better comfort at higher humidity level. You feel good at lower temperatures if the humidity level is a little bit higher. So you need not to heat your building as high as it would be in a drier conditions. That's due to the due to the effect of the human body, which is cooled by dry air. So you feel colder at dry air and warmer at more humid air. That's one effect. And the second effect is the evaporization of water. Under dry conditions, dry indoor air conditions, you have higher evaporization rate. So you have some more evaporization from flower irrigation or clothes drying or whatever. To feed the energy for this evaporization, you need extra energy. But if you have a higher level of indoor air humidity, you need less. And accounting these effects, there are several more, which I didn't mention. Jürgen Schnieders did a really good scientific work on it, and you can read these papers about these different effects on energy due to ERV. But it's a limited effect, and the number of 0.08 is accounting for these effects, and it's limited to a total of 4.8% and not higher. Why? Because if you have really high humidity recovery, which is 70% or 75%, you would run into problems with overshooting of humidity. So you could rise into problems with mold growth or problems with too high humidity. How to avoid? You need some humidity control. Humidity control means you have to rise the flow rate. You need some extra ambient air, some extra rise of flow rate. Yeah.
So, Rainer, I think we'll get into some of these details within the next session, where we talk about some design aspects. I just wanted to jump in for a second here. I think that we've got an excellent technical discussion, and for better or for worse, we've got an excellent technical panel here. So we can quickly dive into the weeds on product performance and dissection of rating metrics and those kind of things. As I'm taking a look at the questions that are coming in from the audience, though, it seems like some of the issues that folks are really facing on the call is just availability of units and how to source units and specify H and ERV units that will comply with and meet performance goals within passive house buildings. So I was wondering if the panel could spend a little bit of time addressing how, if you don't have a PHI certified unit, how can you use that in the PHPP software and within PHI's program to still comply with the requirements of the program and still end up with a good product for the consumer? Mm-hmm. So, is there someone on the panel that feels like they're in a good position to field that one?
Yeah, the easy way is just to ask for the exhaust temperature and ask for a test under flow balance conditions. So if the unit already has some flow balancing automatically, it's all is good. And then if you get additional information of exhaust temperature, then you can calculate it with this formula for yourself. And then you have pretty well this number you need to calculate the balance.
Okay, so in doing that, and maybe there's someone who's a practitioner on there that also can speak right now. It would be really helpful, I'm sure, to walk through an example, and maybe that's something, Ken, that NAPHN could provide afterwards. Maybe just a cheat sheet or short list of, hey, here's the situation. I've got a unit that's not PHI certified. How do I put this round peg in the square hole here to get my unit forward to compliance? So that might be an action item that we could follow up with here. Another question that I'm seeing from the audience is how many manufacturers at this point in the North American area or the North American continent are PHI certified, and do we see momentum in that direction? What availability do we have at this point for a broad range of selection? Ken, maybe you're aware of that, or Andrew, if you're on the call and can speak, or maybe there's someone from NAPHN who can direct users to where they can find a list of available products.
Sorry, Mike, what was the question? I've been following the chat.
Oh, sure. Yes. Thanks, Andrew. Sorry to pull you out of the chat box there. So the question is, what units are available today? How many manufacturers are providing units that are certified as an HRV, as a product? And where can they find those? Where can users find a list of these? And do we see momentum in that direction?
Great. Yeah. So there is still only a handful of certified HRVs that are available in North America. I know in the chat, a few of them piped in, like Zender and Swigon and Ventacity. And there has been interest from a handful of North American manufacturers. I'm not aware of another one that's, let's say, pulled the trigger on completing the process yet. And so I think there's often a hesitancy because of potential testing costs and uncertainty about the size of the market. Yeah, so it's definitely a work in progress, and we welcome more manufacturers into the discussion, and we just need some to really say pull the trigger and start the process.
Great, thanks. So another question that this really drives home, that the discussion's driven home so far, is just with so many rating metrics, like Reiner talked about in his presentation, how many different considerations there are. And it sounds like a lot of them, like nothing could go wrong, right? With so many things to think about as a specifier and as an installer, not to mention the user side of things. But these are sophisticated pieces of equipment that are doing a great job, made by manufacturers who are delivering value where it's needed to consumers who have a need for this, especially in passive houses. So maybe we can take a step back and just understand, like, how large of an issue are we talking about here for the consumer? Like, what is the ventilation energy use in a typical passive house as compared to, let's say, just the whole building use? As a percent of the total, and how much are these differences in performance making with respect to total building energy usage? Maybe somebody on the panel can address that.
Yeah, for sure. It's around 80 kilowatt hours per square meter and year. So that's more than the energy consumption of a passive house, specific energy consumption of a passive house for heating. So it's really important. And the range between a bad unit and a good unit is, well, the early units with a cross flow, they are in the range of 50%. And the best we measured ever was 90, 95 even, or 93 from manufacturers. Nowadays, so yeah, there's a big range of difference in it, and it's not neglectable. So for you as planners, you want to see what's the effect of it, and you could compensate for it, but it's a really big effort to compensate with insulation. You need really 666 insulation or high efficient windows. There you already have triple glazing and good insulation. You can't do it even better. So the energy of the heat recovery ventilation is crucial. That's for sure.
Great. And with so many metrics out there to think about. Yes, go ahead.
Yeah, this is Charlie. I might add that I've been working in commercial buildings with this technology quite a bit. And you have to remember, too, that even in a not so good building, under design conditions, which is how equipment for heating and cooling is sized, the ventilation load can be up of the load of the building. And this is with a not so good building. So it's really critical to load down to the maximum extent possible, because under the worst heating or cooling conditions, ventilation is a huge part of the load.
Great. That's really good to know. And thanks, Charlie, for chiming in there. And with so many, yes, Matthew, you had something to add?
I just wanted to highlight the kind of difference in the residential versus commercial, and I agree with Charlie that in routine commercial, not so great buildings, the ventilation load can still be a very large component. And in residential and sort of run of the mill reasonably efficient homes. The ventilation load is not insignificant, but it's certainly not the majority of the load. The big transformation happens when you achieve these passive house levels. And now you've knocked down so many of the other energy losses from the building. The only big one left is the ventilation. So then, as Reiner said, then if you want to get to zero or something like that, ventilation is your thing to attack with the highest efficiency you can get.
Great, thank you. And with so many different rating metrics out there for H and ERVs, so many things to consider from a design perspective, is there one critical metric that you guys would point to, or maybe two, that specifiers should really focus on? Understanding there's no composite rating like grade A, grade B, grade C, HRV, that makes it really simple for a designer to specify. What's the cheat sheet for a designer going into specifying an HRV or an ERV? Like, what are the high level things that they should be looking for in terms of performance?
There is one key performance indicator which puts all in a nutshell. On the list of the Passive House certified components, you will find this efficiency, the primary efficiency factor, and this can show you a rating which deals with both the electric efficiency and the heat recovery. It puts all in one value. I think that's good, because otherwise you can't see it with one number what is better, what is worse. One has a higher heat recovery, one has a higher electric efficiency, but which unit is better for your purpose? So this one unit key performance indicator could be a good a good rating issue for simple way of rating it.
Matthew, your thoughts?
Yeah, Reiner, can that metric be used directly in the energy balance calculation?
No, that not, because in the energy balance calculation you need the heat recovery rate, and you need the electricity consumption. It's only for selection of units, just to compare the units. But if you want to put it directly in the energy balance, you need it separately, because in this primary energy factor rating, there is some assumption inbuilt about the heating efficiency, though the COP value of the coefficient of performance of the heating system, and in your building you might have some different inbuilt. That's the reason why this cannot be directly in the balance. But the values of heat recovery rate and electric efficiency are the way. Sorry, dry air. Sorry.
Matthew, you're muted. Oh, maybe I called on you when you didn't have anything to say. So,
no.
All right, we'll move on to. Go ahead.
I was just making a pleasant observation. I'll need hydration shortly as well as Reiner.
This is Charlie. Right now I've been working for quite some time on load-based testing of other kinds of equipment, and we're just kind of beginning to look at the load-based testing for H and ERVs. That kind of testing tends to yield a seasonal coefficient of performance, and we've discovered there's quite a large difference in that number in the heating and the cooling climates. That number will be quite different in Georgia, for instance, in North America than it will be in Montreal. And so we're kind of interested in the performance of these things seasonally, in a wide range of conditions, in a wide range of climates. And trying to characterize that right now in North America is very difficult. The test and rating procedures don't really give you that data that you need. So we're just, for the commercial products, we're just starting to work on that. We've applied them to heat pumps so far. We're just finishing up that work after 6.5 years. And we're starting, and it's been applied to rooftop units for commercial. And it's being applied to air-to-water heat pumps. And now we're starting to look at the H and ERVs to see if an HRV or ERV that has multiple functions, how does it operate under its own controls in a typical load in a one of, well, we're using 8 climate zones, things that we do. How will it perform overall on a seasonal basis under those conditions, under its own controls? And that can be a different kind of thing. And we can't find those numbers in North America right now with the test procedures that we have.
And will that be published, Charlie?
It will ultimately. EXP07, which is the heat pump and air conditioning standard, will be published this fall. But we're taking advantage of a lot of the work we've done there for those types of products to apply to the H and ERV. It'll be a lot faster. I think probably it'll be published in the fall of 2022, perhaps. And it'll be published for public review before that.
Great. Let's try to get back to some more of the questions from the audience here. Thank you, audience, for being here. I wish that we had you all in a room and we could ask, what your specific interests are. Unfortunately, we're a little limited in how much we can interface through this means, but hopefully soon we'll all be back together again. So one of the questions from the audience is, what are the optimal air changes per hour when you're designing your mechanical ventilation system? And does this vary based on building use type? Is there somebody from the panel that wants to take that? All right, hearing none, I'll jump in.
Residential or commercial?
Standards that are out there. ASHRAE 62.2 is one for dwelling units. And that's kind of the standard of the reference consensus standard in the U.S. There are also requirements within the building code, the International Residential Code. International Mechanical Code has requirements. The Canadian Building Code is a source since we're talking North America here. And of course, European standards as well on ventilation rates. Generally, when you get into tighter homes and tighter buildings, you're increasing the ventilation rate to drive similar air changes. And so it's important, it becomes increasingly important to recover the energy from exhausted air because you're moving more air through that ventilation system at that point. And so, as Reiner said, you hit this tipping point where your ventilation becomes even more important than your heating in certain cases as far as total energy use. So that's where I would point the inquisitor there regarding that question. Okay, another one for the panel. Is it better to design and spec your ERV based on wintertime conditions or summertime conditions? And when should an ERV with moisture recovery efficiency be considered for a project? Additionally, are there any specific ERV strategies for hot, humid climates that should be considered?
So it's good in both cases. So in wintertime, you reduce the need for humidification, and it's good for health reasons. So North America, cold climates, really a relief in indoor air humidity. You save also energy for defrosting. That's a good idea. But at the same time, for the humid climates, in warm and humid climates, if you have the need for dehumidification, then you do it with heat pumps or whatever, with a lot of effort for electricity and installations and so on. But then with an ERV, you could keep it as at a low level. So the low indoor air humidity is kept low via HRV. And that's a really good idea. These are combined systems of dehumidification actively plus passively by these HRVs. And that's in combination a really good total system in terms of energy efficiency.
Thanks, Reiner. Here's a great question. Are unitized ERVs, meaning ERVs that would serve like a single dwelling unit, more or less efficient than larger centralized units? And I would assume beyond just the recovery efficiency, one large consideration would be duct systems and fan energy usage. So I'll open that up to the panel to see if there are any good resources there or comments.
Yeah, there's some physical key issue. Big fans are much more efficient, so the flow efficiency is higher. On the other hand, you have a higher pressure drop in the ductwork because the ducts are longer, mostly smaller in relation. So it somehow compensates. But in any case, you should reduce the pressure drops to a minimum. That's always a good advice. Though I would say there are other reasons for preferring the one system or the other. So it's not a reason of efficiency. It could be in both cases high efficiency, so a high efficient centralized unit or a high efficient lower unit, a smaller unit. It's more on practical issues like maintenance. Do you want to get into a dwelling for maintenance of a single unit, a smaller decentralized, or do it centrally on the rooftop or whatever? These reasons are more important. The efficiency can be just the same and high in both cases, central and decentralized. It's no preference of one or other.
Great. Question, let's talk about sound requirements. Obviously, there are sound requirements, testing requirements, or maybe not so obviously. It's difficult to interpret the PHI's testing requirement and certification requirement with respect to sound. It seems like there's this 35 decibel requirement if you're above 35 decibels or above 25 decibels, you can't be in a living space. You can't install the ERV in a living space. If you're at 35 or above, you can install it in a mechanical room. I was just wondering, how were these limits selected? And were there studies out there or something that showed consumer acceptance? And maybe you could help us understand what is absolutely required versus what is a nice to have in terms of using non-PHI certified units versus PHI certified units.
I would say for comfort reasons, nice to have would even be even lower. So 25 is okay. It's really low sound. But there are really good units on the market already, which can be already lower, and you always can have it lower with better silences. So you have to distinguish from the direct sound from the unit, from the casing of the unit, and where to place the unit. So these threshold values were from practical issues. The question where to place the unit, if it can be closed somehow, some sound protection, then it doesn't matter so much. But if it's somehow connected to the other rooms and or living rooms or whatever, where you need a low noise level, then it's really good to have a low sound level sound emission from the unit itself. And the sound transmission via the ductworks, you always can reduce to that value what you want to have. Just invest more money and space for silencers, then you can reduce it. And the total system will be cheaper and easier and smaller if the unit itself already is very low in sound emission. So that's the advice. Either you invest in a low sound system or you invest in silencers. You can do both. But you need to know the values. on the ducts, what are the emissions of the sound on the ducts, and what is the emission of the casing.
And non-PHI certified units can, without sound results, can be used as well, right? Within the PHI program?
It can be used, but then you need to know how good the silencers should be. So you could test it to yourself, but that's a big effort. So as a planner, you want to know the values in advance. So otherwise you run into problems on the building side. If the sound level then is too high, how to enhance? Then you add an additional silencer or whatever. That's not so easy on the building side.
Got it. Yeah, I was just trying to figure out where 35 decibels and 25 decibels fell with respect to other appliances out there. And so I looked at Energy Star dishwashers, for example. And the best dishwasher I could find out there was 39 decibels. And those, I don't know if you have ever heard the Mielis. I've been in a room with one of those running, but it's very quiet, almost imperceptible. And those are at 39 decibels. And so 35 is, yes, Berthel.
Well, be careful. A dishwasher is not running 24 hours a day. And your ventilation system is running 24 hours a day. And the point is, if you want to sit on your sofa and read a book, the noise from the ventilation system is annoying. And noise is the most important thing why people refuse the ventilation systems. This is our experience from Germany, because noise is always present in your living room. Yeah, energy is a second part, and energy efficiency and so on. This is technical, but noise, you feel it. Yeah, so please be careful, and you make your people unhappy if you go for too bad silencer or you forgot your silencers.
Good perspective. Yeah. All right.
Maybe I'll jump in. It's Andrew. It's important to point out that with the levels of insulation, air tightness, all that, the amount of noise coming from the outside into the dwelling is much less than conventional. Yeah. So occupants of a passive house hear noises more than they normally would.
And this is again the point
and
with
the test and rating.
With office buildings. In office buildings and meeting rooms, you have a higher noise level anyway. And there, maybe sometimes it's not so important. So you can accept for a higher noise level from the ventilation system. But anyway, there, I would recall the 25 decibel. It's a very good perspective. Yeah.
Yeah, it's amazing.
Reference.
Are there similar noise requirements on the heating and cooling system? I haven't looked into the requirements there, but do you guys have similar requirements there?
Yes, for heat pump systems, we say you should go for this 20. You should keep the 25 decibel as well. And as Reinhard pointed out, if you have a good silencer, you will be able to do it. You have this. You need the spectrum of the noise source, and you need the spectrum of the noise reduction of the silencer. So, and you can. It's engineering. It's just noise addition. Yeah. Well,
we can do anything we set our minds to, right?
Yes.
Another question from the audience here. More very large-scale projects are going to passive house. Many of those buildings need to consider custom ERV solutions. Not sure why, but that's the claim. Has PHI considered how to handle performance of custom-made units? So this goes back to Reiner's early days, I think, right? With out of Sweden, the earliest models?
Yeah,
homemade.
About custom-made things, maybe. And you're right. This in early time we had no other things already. The custom-made things may work, and the engineers they may succeed. But the point why we recall for the certified units is, and for the already tested units is you can rely on that. Yeah, if you do not have parts. Who can you rely on? there's some risk left. Does it work afterwards or not? Yeah. So you may be successful, but well.
Here's another question about keeping fan energy as low as possible. How do we do that in terms of design and installation?
Yeah, the first thing is to keep the pressure drop of the complete ductwork low. The second is the unit itself, the cross sections within the unit, the pressure drop of the heat recovery system should be low. Keep the areas of the filters large to have lower pressure drop. And then, last but not least, the efficiency of the fan itself should be as high as possible. So the electronically commuted fans are high efficient, and larger fans are more efficient than smaller ones from hydraulic efficiency. Yeah, that's the steps to do. And then it's a control. If you adapt the flow rate to your needs, so if you have not so high flow rates necessary because there are not so many people in the building, then you can reduce the flow rate, and the energy goes by a power of 2, power of 3 in the consumption. And yeah, that's how to reduce the electricity consumption. That's the best way to do so.
Great. Here's one that's really pertinent that we've all been dealing with, over the past 18 months or so. And one of the initial concerns that I saw even coming out of ASHRAE and their early guidance was if you have an HRV, disable it because there's a potential to transmit COVID across the heat exchanger, the COVID virus. So that was initial guidance that was proposed by ASHRAE, but then they walked that back. And this question's kind of along that same vein. It says, in the post-COVID environment, should we be concerned with potential virus particles being transmitted through a ventilation system throughout the building? And what are strategies to reduce this potential?
So the best thing is to use the ventilation system and to reduce the concentration of viruses in the building. So even if you have some leakages within the system and you would have some transfer of viruses, it's still a diluted concentration of viruses. So ventilation is a good preventing method for infection by viruses. So as we mentioned, the criteria for the leakage rate, it should be lower than 3%. It's a really, really small amount. And you dilute the concentration of viruses indoor if you ventilate well the building. So the best way is to use it, and even in future we should enhance the knowledge about ventilation to reduce the risk of infection by viruses. What you should avoid is recirculation air, because then you mix the viruses all over the building. But what we have here is just outer air coming in, going into the building, and you extract the air from the extract air side. There is no cross-contamination, and you dilute the concentration of the viruses.
Great. So I think we're almost out of time here for the panel, but I just kind of want to put a bow on the discussion that we've had so far, and to thank, of course, Rainer for presenting and all the rest of the panelists for their expertise and lending their time here. And the ventilation discussion will go on not only in the next symposium forum here that's on the schedule, but also as we go off to our 9-to-5s after this and are faced with these design challenges. Hopefully we can provide better resources. The industry can provide better resources to you as specifiers regarding selection of units and their specification and installation. It sounds like one of the pieces that's missing that came out of this that the audience wants to see is better guidance on how to use non-PHI rated systems within PHI's program, what to look for when you're specifying a different type of unit, and maybe the minimum criteria. I heard Reiner saying in his initial proposal his initial presentation that that the performance of units was pretty low when they started off, and gradually we've seen improvements, and they're more and more we're learning more and more and developing more and more with research and development, and getting to where we can set minimum criteria and say, hey, nothing below this bar. And I think that the building codes are starting to catch up as well with stuff like that, like minimum fan performance in the International Energy Conservation Code is 1.2 CFM per watt right now. And that's very nearly at PHI's minimum performance of roughly 1.3 CFM per watt. So that's just one example. Codes and standards are setting minimum SREs and ASREs. We've got Canada setting minimum, not setting minimum performance requirements, but requiring testing within their regulatory environment at this point for units sold in the country. And so we're seeing a lot of movement here and continuous improvement. So it seems like it's really incumbent upon us as the industry to help provide the materials necessary to get you guys the tools that you need. So I'd just ask the audience and the rest of the time that you have here in the chat to let us know how we can help you with the components that you need to specify efficient and comfortable, as Reiner said, ventilation systems looking forward. And I think that's about all the time that we have for today. So Ken, should we turn it back over to you for any guidance on how to transition here to the next session?
Thank you for coming. All right, I'm going to hopefully not touch on too much stuff that Reiner talked about before. I am going to just give you the brief how we understand it, the requirements for passive house ventilation, and what we've been seeing on our projects, and sort of any issues that we're having and lessons learned at the end there. I'm the director of passive house services for Stephen Winter Associates, for those of you who missed the beginning, and our niche is really large scale, kind of difficult projects. So we're kind of in the big building realm. So just to go over the basics for passive house here, it's definitely and I stole all of this stuff. I plagiarized it from Passipedia. So if anyone has trouble with it, it came right from the horse's mouth. So fresh air is definitely not just a matter of comfort, but it's necessary for health. Everyone knows that. And so it's the key technology for all of our future residential buildings and retrofits, right? It's very important, as we've discussed today. And I think, as some of you may have seen in the chat from me, we're having a really hard time in the US getting good units, but that's not stopping us. There's millions and millions of square feet of passive house projects underway with this problem. So don't let that stop you from doing passive house. They will end up saving considerable amount of energies if you can get efficient airtight systems like we were talking about in the previous session. And the real goal originally about providing these types of ventilation systems and creating the passive house standard was to reduce the loads on the building so low that we could actually use the ventilation system to provide heating, right? So we wouldn't need 2 sets of ductwork, which would help keep the costs down. And so in order to achieve that, you would actually have to get the heating load down to about 10 watts per meter squared. And I'm going to show you sort of what's happened to us in the Northeast here for our particular projects, and we can go from there. I know it's a little bit biased to cold climate for this presentation, but that's where we're having some issues, I think, really, is in the cold climate realm in particular. So here's the basic requirements for flow rates. I'm sorry I didn't put it in SI as well. So on the supply side, we want a minimum boost rate of 18 CFM per person. I believe that's equivalent to 30 cubic meters per hour. I think that's similar. Okay, and then for kitchens, minimum boost is 35 CFM. Bathrooms is 24. You get the gist. Now, depending on the size of the property, whether it's a single family home or multifamily dwelling unit, we want to make sure that the daily average flow rate of that ventilation is no lower than 0.3 air changes per hour, right? We want to make sure we have adequate ventilation on average throughout the day. So there's additional guidance on Passipedia for very cold climates where the relative humidity is going to go very low. And if you put too much ventilation in a cold climate in very cold temperatures, you're going to wind up with excessively dry air. And the chart on the right sort of shows you where we fall with excessively dry air. Where you have as many health problems, if not more, with very dry indoor relative humidity than you do with overly moist air. Right, so the optimum range is somewhere between this chart says 40 to 60. I've seen 30 to 50. Me personally, I would like to see somewhere around 40%. I think that it alleviates a lot of the indoor relative humidity or the condensation problems you're going to have, but also is enough for a healthy respiratory system. So we want to make sure humidity levels don't go any lower than 30%. Passipedia says to help achieve that, you can go down to approximately 0.25 air changes per hour, is a little bit lower than that 0.3 before. And that's just in this cold, dry weather. And the supply air per person should really go no lower than 20 meters cubed per hour in those conditions. Okay, so those are some basic parameters. Now what we find here in the cold climate is that this is a page in the PHPP. This is the heating load page. And this tells us whether we can actually use the ventilation air as it's designed to provide the heating to meet the heating demands in the space, the heating loads. And if we're talking about a single family home in the Northeast, in Canada, in colder climates, we're really not able to reach the heating. We're not able to use the ventilation system. And the reason why is we get two ways to certify, right? You can either choose the heating load method and try and get down to that 3.1 BTUs per hour BTUs per hour as far as the heating load goes per square foot, or you can use a heating demand method, right? And that's the annual demand for the building. And in the Northeast here, it's easier for us to meet the heating demand level because our peak loads, our peak temperatures are very drastic. So getting that heat load down that low is much harder than meeting the heating demand set forth by Passive House Institute. So we generally don't have enough flow in our ventilation system to meet the heat load under peak conditions here. And so, in order to do that, we would have to really, really jack up the building past what we would need for normal certification. And we really don't have a good magic box for unitized HVAC anyway. We don't have a really good, and we don't have a number of options to choose from where we can just provide the heating and cooling with the ERV on an individual basis for a single family home. All right. So on the cooling side, in cold climates. So what we find is that larger scale buildings, commercial buildings, multifamily buildings that are more dense are actually cooling dominated. They're not heating load dominated. And so we have to look on the cooling side. We're going to have a higher cooling load than we are going to have a heating load. And so what we're finding, this is from the cooling loads page, is that for our multifamily projects in the Northeast, we actually don't have enough ventilation air to meet our cooling loads. All right, so I'm going to talk primarily about multifamily larger scale buildings. So, this is where we're headed, right? So we don't have enough ventilation air to meet our cooling loads. And cooling's even harder to get down in these multifamily high dense buildings than heating is, right? Heating's a little bit easier to deal with than our cooling because we've got all that internal gains, all those people per square foot. So we're really looking on the cooling load side. So what we see in our multifamily buildings is that exhaust flow rates per code are higher than required on the supply side, right? So our exhaust design is actually driving our ventilation design. We have a minimum ventilation rate that we have to meet for our bathrooms and our kitchens that's generally higher than the supply requirements for occupants. So that's usually where our system is sized. We also generally tend to go with constant volume systems in these large scale buildings because we're going with central systems. And I'll show you a pros cons chart on why we go with central for our multifamily buildings compared to, and that's us in particular, but that's where we're pushing our clients. And so when you go with a central system, there's very few options for providing a boost in an individual apartment that allows them to boost their system. Plus, our exhaust flow rates are actually higher than the boost exhaust flow rates recommended by Passive House. So we wind up with more ventilation than is even required by the boost in Passive House. So there's really no need to provide them with a higher flow rate than we're actually providing, right? We're already over the limits. What we do see is car dampers, constant airflow regulating dampers, put at all the registers to ensure that we can get a balanced central system. And we also see a system called AeroSeal, or an equivalent sealant system, where the ducts are pressurized and we're pushing a sealant into the ductwork that's sealing up all of the seams and the cracks and the holes. Everything up to a quarter inch can get sealed with AeroSeal. The last two bullets are not required by Passive House in any way. However, you will not balance a system, a large-scale system, without these two units, and you will not get the flows you want at the ERV to be within 10% and to be low enough to have an efficient system if you don't use AeroSeal and car dampers, right? If the AeroSeal is crucial to make sure those ducts are airtight. And so here's a picture on the left of what a constant airflow regulator looks like. It's based on pressure, and there's a foil in a damper in there that reacts like an airplane wing to pressure, and it adjusts at whatever pressure is behind it to give you the flows that you need. On the right is a report from one of our AeroSeal contractors that shows that the leakage in the ducts started up here, and by the time they were done, there was virtually no leakage in the system at all. And that's really what you want to see. So we put this in all the specifications and we make a requirement on all jobs, or we really just walk away because there's no way. We had one contractor say, no, we can do it. We can get it to be where we need it to be with just the mastic tape. We said, okay, but we have to test the duct leakage when we're at the end to prove that you did this for the owner. And we tested it and it was a complete failure. It was hundreds and hundreds of CFM leakage. So they wound up having to do this anyway. So I'm telling you, you're not going to do it by hand. All right. Central versus local ERVs. We push all of our multifamily projects to central ERVs. There's pros and cons for both. On the pro side for an individual, you have the resident meter, right? The energy use is on the resident meter. You can use boost control, right? You can give them a little more control over their system with an individual system. However, for an individual system, what we've seen is there's 2 penetrations per apartment. There's in-unit maintenance. You have to get into these units at least 2 to 3 times a year to clean them. You have to be able to clean the exterior grill. And then the potential for condensation on these ducts is incredibly high. I know you saw some beautiful ERV ductwork pictures from Reiner before. That is not the way our ducts look in the United States. That's not, they're like a work of art in Europe. And I have a couple pictures I can show you. And then we have interior RH concerns. In a central system, we feel we can control the relative humidity on the central system before the air is supplied. There's some post-conditioning you can do to that supply airstream where we can definitely bring that, we can significantly control the relative humidity that's being supplied to the spaces, particularly in the summer. There's also reduced maintenance on the central ERV. You've got, they're outdoors or they're somewhere where the maintenance people can get them. They don't have to rely on the occupants. And there's only a few of them as opposed to hundreds, right? We have hundreds and hundreds of apartments in some of these buildings, upward of 300 and 400 apartments. We can't be sending the maintenance in 2 or 3 times a month to clean all of those filters. And then on the con side for central ERVs, you have, this is now on the owner's meter, so they're paying for this. There's a complexity of controls. If you want variable flow rates in these units, it gets fairly complex and costly. There's concerns over stack effect. The taller the building gets, the stronger the stack effect. And can the car dampers overcome that? From what we've seen so far, yes, but the systems still need to be checked and commissioned manually. So this is just a representation of the 2 different ways you can do this, right? The top is an individual ERV showing the 2 penetrations per apartment. And then, you need a taller ceiling because you have horizontal ductwork now that's running through the apartments that might conflict with other systems that are in the ceiling plenum. So your building heights tend to push taller with those systems. And then in a stack unit where we have essential ERV and we just have all these shafts running up the building, you have fire damper concerns that you have to deal with, and you also have floor plate restrictions now that where you're taking up floor space, and you need to make sure, especially in affordable apartments, minimum size rooms are very important, right? So you need to take that into consideration when you're doing your design. So one of the things that I mentioned earlier is that the exterior grills need to be cleaned. This is an intake grill on one of our very first Passive House projects from about 10 years ago. And the owner called us and said her front door was making an incredible whistling sound. And so we're like, oh, something's wrong. It sounds like it's moved into an exhaust-only situation, and it had, because the intake air was clogged. And the ERV actually went from 120 watts to 220 watts at that time. So very important for not just fresh air, but for performance and energy use. On top, you can see filters on an individual ERV in a multifamily building that have never been cleaned or completely clogged. Every time I go into a multifamily unit with an individual ERV, I see clogged filters, no matter how much we tell the maintenance staff. So it's very important, that these get cleaned. Again, you're going to not provide the performance you need. On the right here, this is a condensation thing. This is what Rainer was saying before. If any warm air can get to these exterior ducts, you're going to have a condensation problem. And this duct jacket is vapor impermeable, and it was pushed all the way to the wall, but there was never a finishing tape applied. And as small bits of air got in here and made this insulation wet, it pulled further and further away from the duct, increasing the condensation. So we had to go back and do a retrofit on this. Luckily, there was not significant damage to the apartments. We found this fairly quickly. But this is very hard to do, especially when units are pushed up very high to the ceiling. You can't get around the top of them. So in an individual apartment, they're trying to separate the two ducts, the intake and the exhaust, as far as they can, and they're trying to get them as close to the ceiling and floor as possible, but you can't seal around them properly. So that is a big concern. Now, centralized, we have issues as well, right? We have, this is a really great ERV unit that's telling us we have a recovery efficiency in the middle of winter of 0%. It's a sensor problem. The sensors aren't reading right. We have, installation things. This is from one of our large projects. See this lovely collar here? Well, there's one over here too, or there should be, and it's not connected. So these ducts were aero sealed. The system, we were told, was balanced, and we have a huge disconnect between an actual fan and the body of the ERV, right? So, and this is commissioned, and I'm going to tell you time and time and time again, we get tab reports, testing and balancing reports. Everything's beautiful, everything's fine, and we come and we see stuff like this, right? In the couple thousand CFM off. And we see stuff like this. This tab report showed that this register was actually exhausting exactly what it should have been exhausting, and that's how we found it. So the commissioning of these systems is so crucial. I can't even tell you. You can design the most beautiful ERV system, but if they're not commissioned properly, you're not going to get any good service. So even though we push for central systems, just because theoretically I do believe in the end, once we get this down and we get our contractors on board, we're going to see better performance, reduced maintenance cost, and better control. We still have quite a way to go. So that's my spiel on what we're seeing with Passive House projects in the Northeast. So hopefully you heard that, and I wasn't muted the whole time.
So thank you, Lois. I think the presentation was great, and the presenters of the first session were also great. My presentation today is going to be showing how different components of the building become interconnected when the buildings become so airtight. And I will be basically following up on what Rainer was explaining and what Lois was explaining, and show some examples of buildings that we are monitoring. Our bread and butter is training builders to implement Passive House on a daily basis. So having data from monitored and occupied Passive House buildings is crucial to show them how what this means in the reality of an actual project. So today I'm going to cover on the interdependency of building components, how the selection of windows impacts the selection of the mechanical ventilation system and vice versa, and how design teams really need to talk to one another to avoid moisture-driven damages. We're going to talk about the tightrope walk of moisture management in tight buildings and how we find compromises between the interest of the building and the interest of building occupants, because at the end of the day, it all starts to work as one. And then we're going to look at some monitoring results from occupied buildings, including ERVs and HRVs, and some impacts on project strategies, what can be implemented safely and less safely depending on different climates. So I want to start with a building that is by far not passive house. This is a building that I've been monitoring for about a year. It's a multi-family building, relatively recent, less than 10 years old, in the vicinity of Denver, Colorado. So climate zone 5B, so relatively dry. And there's kind of one of the misconceptions we find often in teaching professionals is that if the climate is dry, then you don't need to worry about moisture. Now, in the past, that was true, but with the buildings becoming more and more airtight, that is no longer true. And this building shows a perfect case. So this is condensation taking place on windows. And the windows in these buildings are nothing but code-compliant windows. You have the isotherms at the top, you see condensation at the bottom. And these graphs on the right show the monitoring over the last month of February, which we got some pretty cold temperatures in the negative digits, which for the city of Denver is not super common. So if you look at the monitored relative humidity at the glass edge, you see condensation taking place frequently during this month. Now, nobody is surprised, or nobody should be surprised, to have condensation of windows when you have extremely low temperatures outside. Now, what is interesting in this monitoring is that we had condensation with mild temperatures, meaning that it was a mild February day, and we had condensation of windows. And the reason for that is the heating system and the ventilation system of these buildings are one and only, and they are driven by the need for heating. So if they are on auto, and if it is a mild winter, then the heating system doesn't kick in, and the ventilation system doesn't kick in. So this is where, regardless of your building passive house or not, we got to a point with even just code-built buildings where you may have moisture-driven damages in dry climates because of a poor strategy for the design in the first place. So in this case, the ventilation fresh air is secondary and subject to the heating system. So something that we need to change in our practice. Now, I call this the tightrope walk of moisture management. You have moisture-driven damages that are not necessarily associated with condensation itself. This image shows wood rotting that does not need the wood to be actually wet with condensation. It's just driven by the moisture content of wood. You can have mold forming on the inner surfaces of the building envelope. Again, no actual condensation, but you can have mold. And this translates to an indoor quality issue for the building occupants. And you can have other issues, including metal rotting, again, not directly related to condensation itself, but to high relative humidity on a constant level. On the other hand, if your building is too dry, you can have your harbor floor can crack, and you have irritation and dry nodes, so it becomes uncomfortable for building occupants. So on the left, we have the much beloved psychrometric chart, and that is the green area here is what we typically try to shoot for. And our suite area, the one that we recommend, is to have the building between 30 to 50% relative humidity. If you have more than 50% relative humidity, it becomes a problem of condensation and or mold on thermal bridges. So we recommend not to have the building exceed 50%. And so this is kind of, if it is too humid, you have higher risks for the building. And if it is too dry, then you have lower comfort. And as a designer, you find yourself like trying to walk the line between the two, compromising building and people. So you do want to provide comfort for people, but not at the expenses of exposing the building to higher risks. So this is where you come to a crucial decision point as a designer, and this drives your decision in terms of ventilation, among other things. So what drives moisture, the moisture balance in a building? I hope everybody knows that the climate does play a role. But as I was showing you earlier, even in a dry climate like Colorado, that is just one part of the picture. Another part of the picture is the occupancy. And we typically design with standard occupancy, crossing our fingers and hoping that we do get normal occupancy. That is not a given on a project. We have design considerations. On the left, we see the ventilation system as well as the balancing of the ventilation system, meaning that unlike conventional ERV and HRV system, I believe Passive House has a much better quality assurance process because it requires this system to actually be balanced room by room and register by register, which actually gives you hope that you do get that ventilation rate that you were hoping for. You have execution. You want to have your building airtight, and you test it with a blower door test. But also, you have a hope to have your construction coming at the end of the construction process being fairly dry. Fairly dry means that everybody involved in the construction were diligent in trying to keep the product dry and having a good installation. So at the end of the construction, your building is dry to begin with. Now, there are some wildcards that we as designer cannot guess. Just the use of one humidifier in a room can completely throw these design assumptions off. So we do want to have kind of a built-in moisture resiliency in our buildings because we don't actually know what's going to happen inside them once they are occupied. So I'm going to compare now two passive homes that we have designed and monitored over the years. This one on the right-hand side is actually in Europe. It's the equivalent of climate zone 4A, so it is the PHI warm temperate climate. It is a mixed climate, still predominantly heating dominated, but it is fairly humid, and it does require active cooling and dehumidification in the summertime. 2 people every 800 square feet. It is a masonry building with lime plaster, which does impact the moisture profile of the building. 0.35 at the blower door test has an HRV with 135 CFM, and the CFM rate here is at the upper limit of what is allowed for passive house because it also supplies the building with the active heating and cooling and dehumidification system. 92% PHI certified sensible heat recovery and 0% latent recovery because it's an HRV. It only covers sensible heating. This is another project located in Montana, climate zone 6B. It's cold climate for PHI. It is a dry climate, more typical occupancy for person building. It's a stick frame construction with mineral wool insulation on the walls and cellulose on the floor and the ceiling. 0.14, it's a very tight building. It has an ERV ventilation system just used for fresh air, so the ventilation rates are actually lower in average. 83% sensible recovery and 71% latent recovery. So 2 passive homes that are occupied, but some significant differences not only in the climate, but also in the occupancy and in the ventilation strategy. We have monitored these buildings by opening them up, opening the HRV and ERV up, and inserting sensors inside them just to keep track of temperature and relative humidity. The data that I'm going to show you now is fairly accurate, not as accurate as you would need in order to certify a unit. But again, what we're trying to do is show builders how these things work in reality. So it's more the order of magnitude that we're trying to show here. Don't try to this at home. Don't open up your ERV or HRV unless you want to, unless you are qualified for that. Looking at adjusted temperature, on the right-hand side, we see the HRV used in Europe, and we see a significant passive heat recovery. This is an HRV that has a PHI certified heat recovery rate of 92%. So it is able to passively preheat the incoming intake air from about 35 degrees to about 70. So significant less heating needed by the heating system. And on the left side, we see the ERV system used in Montana. And you see this, it's a two-step process here because we have a geothermal preheat for frost protection, which preheats the temperature and kicks in about 10 degrees before the actual passive heat recovery takes place, adding another 20 degrees to the heat recovery. So different strategies, both in terms of moisture recovery as well as frost protection. What about moisture? We've been talking about condensation and how to maintain a good balance of moisture inside the building. So on the right-hand side, we see it is an HRV system, so it has zero moisture recovery, resulting in condensation taking place inside the heat recovery core. And this is shown on the right-hand side here. Whereas in the ERV system, there is no condensation because the unit actually recovers the moisture. And this is shown by looking at the absolute humidity inside the ERV. Here on the left, we see the passive moisture recovery taking place inside the ERV, whereas in the HRV, the moisture recovery is negligible. So this is something that you need to build into your thought process and in your design strategy, because your climate as well as your occupancy may drive your decision. So if you are in a very humid climate, you do want to have an ERV system to keep the moisture out. So that passive moisture recovery would actually go the other way around, but keep the moisture out. So if you're in Florida or Alabama, some places that are very humid, that ERV may help you reduce the need for active dehumidification from the cooling system. Again, this is we're trying to juggle between the giving priority to the building or to people. On the left-hand side, we see the relative humidity in different rooms of the passive houses in Montana. And you see that because of good ventilation strategy, it is never too dry, nor it is too humid. This data is collected by minute, and then I averaged out by 12 hours value. So, you may have a peak of a few minutes if somebody's taking a shower in the bathroom, but then that gets evened out. And this is including some boost mode that the occupants may use. For the unit with the HRV, different climate, the strategy seemed also to be good. And in the case of the project on the right-hand side, this decision for the HRV was made based on the higher sensible recovery. But we see that because it is not a very cold nor a very humid climate, then we can see it was an appropriate decision. So looking at what impact this has on building components, we start looking at wall assemblies, and something that is unfortunately still very popular in the US is the dew point method, which was actually developed in the 1930s or 1940s, so very limited building science at the time. And if you use the dew point method for the walls of this building, the project will fail. Whereas if we have monitors, sensors built inside the assemblies of this project, and what you're looking at on the left-hand side is the green line, the green curved line, shows the moisture content hour by hour monitored over a very cold month. This was this last year, February, where we got at the wall sheeting, we got down to 0 degree Fahrenheit. But the moisture content never exceeded 20%. That is the threshold typically considered to have biological decay, so wood rotting. So there's no condensation and there's no building damage, although the simplified dew point method would say otherwise. So the impact of durability, just to give you another example, this is from a simulation. Looking at climate zone 5B here in the West, typical of Denver, for example, the go-to typical ventilation decision for passive house would be the ERV system with moisture recovery. But you may have in your project some assemblies that are more critical than others. This shown here is a concrete basement wall. So it's an assembly to the ground with the insulation all on the inside. And we did some simulation using roofing, using ASHRAE, standard 160 assessment. And if we did use an ERV system, in this case, recovering the moisture, this wall would fail. Whereas if you have an HRV, this wall would succeed and would not have damage. So this is kind of where you need to decide how to compromise between giving priority to people or giving priority to buildings in managing the moisture through your ventilation system. In this case, this was impacting the long-term durability of this assembly. Looking on the shorter-term impact on hygiene and health, we're back to the original building, and we saw how the weak component was impacted by the overall strategy of the building. Now, the weakest component in this case was the window that seemed to be the party at fault, but the party at fault here is really the heating and ventilation system being regulated on the heating demand, so on the heating load versus the fresh air need. So in selecting different windows or different components, you really do want everybody in the design team to come together, because the selection of a ventilation system will impact the weakest component of the building envelope. On the left side here, you see a table showing the condensation on a code-compliant window depending on exterior temperatures and interior relative humidity. So the condensation issue is just one of the different moisture-driven damages that you may have. And you can see that we put this together in form of a table, because it's never just a temperature, it's never just a relative humidity, it's multiple factors combined together. But the more the buildings become airtight, the more all these different components become interrelated. So deciding on a ventilation system has impact today on the weakest components, such as the windows, and vice versa. So to conclude, the more airtight the building, the more interrelated its components become. And buildings are for people. Hygiene and durability goals needs to be a top priority over energy and carbon, in my opinion. Passage air tightness and ventilation should maintain consistent conditions within the building within the optimal range between 30 and 50%. And project-specific critical conditions need to be addressed carefully by the whole design team to avoid issues and problems to occupants and assemblies. Thank you.
So I'm going to kind of continue on what Lois and Enrico both talked about, try not to repeat too much of it, but to focus a little bit more on controls, kind of what are the controls approaches for ventilation systems for a passive house. Again, I'm with Dagger Engineering. We're a MEP and sustainability consulting firm located in New York City. So a lot of what I talk about is going to be kind of focused on the designs that we've been doing in the Northeast, majority of it in the city itself. So to kind of start, Lois touched on this a bit, the differences between unitized systems and central systems, and the kind of how they relate to both single family and multifamily buildings. And I'm going to touch on the controls aspects of those as well. Certainly, unitized systems can be utilized or are utilized in single family buildings, and then they can also be utilized in multifamily. Whereas the central system is more for a multifamily scenario. So just to kind of reiterate the unitized ventilation layout, you would have a single ERV either for a whole house or for a single apartment in a multifamily building. The kitchen and toilet exhaust are combined into the ERV. And I just want to reiterate that what we're talking about when we're talking about kitchen exhaust is area kitchen exhaust. Typically a passive house building would have a area kitchen exhaust in the kitchen itself with a recirculating hood over the range. You would not want to duct your range hood exhaust into an ERV because it could kind of foul it with grease in that. So just pointing that out. Then obviously you have ventilation to each apartment, and then the intake and the supply at the facade. So in terms of ventilation controls options for unitized ERVs, there's there's a bit more flexibility in this because the unit itself is only serving one house or one apartment. So you can kind of control it as you wish, since the occupant themselves has that, ability to kind of adjust the controls. So, obviously there's the constant volume, right, which is sort of that continuous exhaust and ventilation through most of the day. But then typically with a unitized ventilation system, you would incorporate a manual boost mode. So there may be times of the day where the occupant would like a little bit more ventilation, whether it's, they have some people over, or they're cooking, or, taking a shower, or whatever it is. You can kind of manually boost that ventilation to higher levels. Then there's also an option for economizer mode, which is also known as free cooling or bypass mode. So essentially times during the night or in the shoulder season, so the spring or the fall, when the temperature outside is actually cooler than the temperature inside, instead of wasting energy and running your air conditioning, you can bring in that ventilation air, the cool outside air through your ventilation system to kind of cool off those spaces. But that requires bypassing your ERV core or wheel in order to do that. So that's kind of one mode that you can run your system in. And then another option is demand controlled ventilation. So this is often utilized in commercial buildings and office spaces, but you can also utilize it in a single family home or an apartment where you would have the system kind of ramp up and ramp down based on CO2 sensors within the space. And I just want to point out that, you can certainly use these different control options in tandem with each other. It's not kind of a one or the other sort of thing. So you could certainly have a system that has boost mode with free cooling as well, or with demand controlled ventilation. And then moving to central ventilation, essentially within the apartment, you have the same sort of exhausts from the kitchen area and the bathrooms, and then the supply to each living area. However, the difference is now there's a single unit that's serving multiple apartments. So that becomes a little bit more complicated in terms of how you control those units, so that everybody that it's serving has the right amount of ventilation air and is appropriately comfortable. So Lois touched on this a bit, but in terms of central ventilation controls, obviously the simplest is a constant volume system. PHI does really push to have the kind of option for a boost mode, but as Lois pointed out, if you're already designing to kind of those higher levels that PHI recommends, then potentially you could avoid that boost scenario in a central ventilation system. There is an option to have to design for a boost mode. It would be called a variable air volume system, where essentially you are varying that air based on sort of user controls, similar to a boost in a single family or an individual ERV scenario. But that requires basically installing VAV boxes, variable air volume boxes, which sort of the user can kind of open and close those, and then the unit at the roof is going to ramp up or ramp down its fan based on a pressure sensor in the duct. So it's certainly possible to do this, but it does add a significant amount of cost to the system and just complexity. It becomes more challenging to balance the system with this approach and just kind of maintain the system overall. So I haven't really seen that done very often in central ventilation systems. You can also incorporate, similar to the unitized approach, you can incorporate economizer, free cooling, in a central system, but it can become challenging to kind of make sure that you're not negatively impacting the temperature in all the spaces that unit is serving. So you may end up with an apartment that could use free cooling because they have they're having a party, it's hot inside, whatever it might be, but you may have somebody else that just has a single occupant who doesn't want cooling. And now how do you control, when you use that free cooling in those spaces? So typically you don't see central ventilation with free cooling. The better approach really is just to have people open their windows if it's nice outside. Demand control, similarly, you could do as well, but again, it's going to require a lot more complexity in a central ventilation system. It's going to basically require that the system is a variable air volume system. So again, you would have those VAV boxes within the apartments, and indoor air sensors kind of in each apartment, sort of averaging or actually taking the worst case scenario and modulating it off of that. So again, that's typically done more in an office scenario than it is in a residential scenario. And the next option is supply temperature control. So this would basically mean utilizing post heating and cooling after an ERV in order to supply neutral temperature to the space. So you could also do this in a single family home. I think Enrico talked about it in one of his projects where he was able to meet the heating and cooling load just with the ventilation system. And so you provide post heating and cooling in that ventilation system. This is a little bit different. In this case, you really want to be supplying neutral air to these apartments, neutral temperature air. So let's say around 70 degrees Fahrenheit. Because you don't want to impact the heating and cooling loads negatively within each apartment if you're delivering that air at a higher or lower temperature. The exception to that would be if you end up delivering the air very close to the HVAC unit so that the heating and cooling sort of mixes with the ventilation air. And in that case, you would need to account for that load in your heating and cooling calcs for sizing the system or the indoor units themselves, because as was pointed out previously as well, it's best to avoid, if you had like a ducted unit in each apartment, you really want to avoid supplying the ventilation air to the back of that ducted unit, because then you're counting on the heating and cooling unit to supply the ventilation air. And if that heating and cooling unit is cycling on and off, you're going to have some intermittent ventilation. So the ventilation air really should be supplied separately from the heating and cooling unit. So, some options for post heating and cooling that we've used on projects is to incorporate a VRF coil in the discharge of the ERV with a remote condensing unit so that you can use, a heat pump to provide that heating and cooling and avoid gas or electric resistance. And then the last option I have here is a humidity bypass. So this also follows on what Enrico is talking about with issues with humidity in passive house buildings. So I have a couple of slides on this. So just to kind of follow up what he was saying, in these multifamily buildings that we work on, they have they're pretty small apartments, and a decent amount of people could occupy those apartments. So you have a lot of high potential for high internal moisture production, just from the people living there, showers, cooking, what have you. And then, the envelope, the passive house envelope really doesn't allow that moisture to get out. So the only path for that moisture to get out is through the ventilation air. And, in ERVs, the point of it is to kind of recycle that moisture. So in the summertime, it's no issue, right? The ERV is exhausting any moisture from the space, which is what you want. But in the wintertime, it ends up really recovering that moisture and bringing it back into the space, which to a certain extent can be good because you don't want it too dry. But if it becomes excessive, then you get over those humidity points, 40, 50% that Lois and Enrico also mentioned. And then you have concerns for condensation. So, there's some different options to deal with that from a control standpoint that we've looked at on various projects. The first would be sort of a simple approach, which would be to switch cores between the winter and the summer, meaning use an ERV core in the summer and an HRV core in the winter. And this could work well for a unitized ERV in a single family home or potentially a small apartment building. But it, is not applicable to a central system, as well as for a large apartment building. It could be kind of a maintenance issue to have to go around twice a year and switch those cores, and then find space to kind of store them all as well. The other option would be obviously to provide some sort of dehumidifier in the space, but that's certainly not the approach that we want to take, because now we're adding, energy to the building, as well as, there's the capital costs of installing that equipment. So what we've looked at on a few projects for central systems is utilizing modulating bypass around the ERV wheel that's based on the humidity of the exhaust airstream. And that seems to be sort of the best approach that we've found thus far. So basically what it means is that there's a modulating bypass that modulates how much air from the exhaust bypasses the ERV wheel. And this is controlled based on outside air temperature, for one. So it only bypasses air when the temperature is below a certain set point. And that set point is kind of based on modeling that's done to see when condensation is going to be a risk based on the performance of the envelope. It's also based on then how much humidity is seen in the exhaust airstream. It's not perfect because it's a blended humidity rate between all of the apartments that are connected to that ERV, but it's certainly better than nothing, and it could be adjusted over time, kind of as you see how it's working, whether it's lower it or raise it. And then, controls the supply air humidity set point, basically. So this certainly can help, reduce the high humidity levels in the apartments, but there would be some reduction in sensible heat recovery because you are bypassing a portion of that air around the ERV, a certain number of hours. But the idea is if you control it based on outside air temperature, so this only occurs, when it's colder outside, and when the exhaust air humidity is high, hopefully it's not for very many hours of the year. And Stephen Winters has done some work modeling this, and it looks like it on the projects we're working on, it shouldn't be too many hours of the year. So there shouldn't be too much of an impact on the energy. So I just want to point out that a lot of these controls options are available as standard options with many of the manufacturers that are out there, both the passive house and non-passive house manufacturers. So for the unitized, it's very common to see equipment with the boost mode, economizer controls, demand controlled ventilation controls. And then with the central system, the integrated humidity bypass is something that we've worked on with manufacturers. So they are starting to come out and make that a little bit more of an option on their equipment. And then certainly VAV, economizer, and demand control are all readily available with the central systems. So in terms of our experience, our recommended controls options on the projects that we've worked on for unitized, single families, what we typically see that on, or maybe a small apartment building, to, incorporate the boost and the economizer for free cooling. Makes a lot of sense. And then typically for multifamily buildings, we're utilizing central systems that are constant volume. And a lot of them do have the supply temperature control with the post heating and cooling and the integrated humidity bypass. So that's all I have. I will stop sharing, and then I think we're going to a panel discussion.
Okay. Well, thank you all three of our speakers. Some great presentations, a lot of food for thought, great experience shared. So I think I'll start. There's a few audience questions we've collected, and I think I'll start from the first one we received, which was from from Gal. Sorry if I've got your forgotten how to pronounce your name. So this would be probably more directed at Lois, but I'm happy to have anyone answer. When you specify car dampers for ERV, HRV systems, what tolerances do you accept in flows from design values?
Tolerances do we accept? We actually don't. That when we go in the field, commission them, we expect to be at least the minimum flow rate that we specified, especially in the exhaust situation. So like supply can be a little bit, as long as the totals are pretty close, but we don't get too crazy about this. What we do specify for our clients that we really want to see it's an adjustable color. Because even though they're supposed to be magically, we can adjust ourselves based on the pressure, they're supposed to automatically come that way from the factory. A lot of times they're not exactly where they need to be, and so to have an adjustable one saves the day.
Okay, great. Anyone else have any comments on car dampers? Any experience with them? Okay, great. Well, I'll go to the next question from Sarah. Could you combine the ductwork for space conditioning and ventilation if you just perfect the flow rate for the specific environmental conditions occurring at the time? Anyone want to handle that?
So I think in certain scenarios you can combine them. The issue becomes that really if you're going to do that, then you kind of have to put your heating and cooling equipment so that the fan is constantly on and not intermittent. And there is sort of an energy component to that, to have that fan running continuously as opposed to cycling on and off with your heating and cooling load. Because if you don't do that, then your ventilation really isn't being distributed continuously to the space. So we have done that in certain scenarios. Again, that's more in office environments, I would say, than in residential. But typically, we would separate the two.
I think another issue too, Josephine, is if you're looking at a single family home too, a lot of the passive house heating loads are smaller than the smallest equipment out there. And so you have to provide a certain amount of flow over a coil. I think, for manufacturer recommendations. So you might actually have to oversize your ventilation system, even though your heat load's not that high, just because of the size of the equipment that you're getting. Anyone has any contradiction to that? But I think.
Yeah, I guess there's two different ways to look at that question. One would be can you use your ventilation system kind of as heating and cooling? And certainly in our climate in the Northeast, you typically can't do that. But then the other would be if you could kind of feed the ventilation into the back of your heating and cooling unit, which has its own fan, which is sort of what I was speaking to.
Gotcha. Yeah, you're right. This is two different scenarios.
Mm-hmm.
We've actually had experience with that, both practically and kind of theoretically. It was actually the production facility where we worked on, which had office uses, a variety of uses, and because of the initial design, they didn't allow ductwork for both heating and cooling and ventilation. So they said, okay, well, we're going to have a ducted heat pump system. We're just going to duct our ERVs into the space, and so that then forced us to run the heat pump fans continuously. And yeah, there was an energy penalty. This wasn't monitored, so we don't have can't measure the impact. But when we've done calculations to see, kind of in theory, if you had those heat pump fans running for the time that you don't have heating and cooling, but you need it for ventilation, we assumed, let's say 50% of the year they're going to run in ventilation only mode. It was about 5% of the energy budget on a multifamily project. So it was, even though, it's like a 30, 40, 50 watt fan running continuously times, 100 units or whatever you have in the building, it's quite a bit of energy.
Mm-hmm.
Yeah.
Okay, next question.
I think Bertold was trying to talk, but he was very quiet.
Oh, is he? Okay. Oh, Bertold, it's very quiet on your end. I think, do you have your headset
Sorry. Yes.
There we go.
Sorry.
There we go.
Sorry. If you go for a residential and think about the compact system and use it for cooling as well, you are in a combination for ventilation and heat pump system, and having running both in combination. And we have some experience with that, as the Chinese apartments, they like to run it like this. And the challenge is to have all the pressures balanced. So you have a circulation mode for if you need cooling, and you have a pure supply air and exhaust air mode. And combining this is somehow tricky, as you have to control your dampers and all the pressures. But we are quite, we think it's quite promising if you have everything in one system, and you design it from the beginning and check for everything. So have it in one box.
I think, yeah, great, Berto. Just to clarify the circulation comment, because there can be confusion between recirculation, which is typical in North America with units that recirculate for frost protection. What you're referring to is recirculation of taking air from a supply room, bringing it back in and kind of cooling it extra and then putting it into the supply air, not kind of recirculating any exhaust from the building.
Yeah, that's true. Thank you. Well.
Okay, next question. I'm wondering if Josephine or others have had any success with VAV, example, Swigon controls for central ERVs. Sounds like not much.
Yeah, we have not designed a central system just because of the costs. We have looked at it on some non-passive house buildings that are kind of higher end condominiums. But even there, it just didn't make sense just because of the costs and the ongoing maintenance, as well as I think the balancing becomes tricky too, because it's constantly changing. I don't know, Lois, if you have any comment on the balancing aspect, but I would have, especially in a vertical system, now you're working again, you have the stack effect in combination with these VAV boxes, and you couldn't really incorporate the car dampers. So I think it would be not impossible, but certainly challenging.
Yeah, from what I understand from Swigon, they're pressure regulated too, so they should be pretty good from that perspective, but it is a cost issue, and most of our large-scale multifamily projects, you can imagine the VE things that happen, and we're lucky we get to keep ventilation at the end of the day, So we haven't had success doing that. We do want to see these capabilities that Swigon has, because it's promising. In some of our smaller multifamilies where the apartments aren't, we don't have to have the ventilation is high, right? It's not, exhaust isn't overpowering the whole system, so we could possibly provide a more balanced, controllable system. But
somebody, Scott, asked a question about boosting central systems based on a time schedule when one knows exhaust needs are more critical. Again, that could be an option to kind of look at what type of building you have, what people's regular schedules are, and provide a boost based on that. Again, you would have to have sort of a 2-position car damper, because your car damper is set to 1 CFM, so it would require a little bit of extra cost there. Maybe not as costly as a full VAV, but it could be an option. I mean, again, I think Lois's point that the CFMs that you're providing are kind of more than what the boost CFMs may be in a single family home, that it may not be worth it, but it's an option. So some latent efficiency values. I have to go back and look where that came from. I think it's from definitely a wheel system, potentially. Yeah, it may have been Swigon, but I'd have to go back and look. But I know their systems are very efficient.
We see that high of a efficiency in the summer quite a bit.
Yeah.
Yeah.
Have you used zone register terminals? Yeah, so a ZRT is what you would use if you were looking at a VAV. That's one option for a VAV system. But again, it's just more expensive.
Yeah, I just anecdotally, we when we first did Cornell, which is almost 8-9 years ago now, it was the first multifamily we did, and we looked into ZRT system, and it needed a pressure sensor in the duct as well. And when we tried to get it priced, no one would price it. So we're like, this is not going to work. I'm sure you can get them to work, but no one wants to cut time.
Fair enough. Yeah. And again, the only projects that we've really looked at anything like that on are like high-end condominiums, which aren't even passive house projects. There's a question here that I don't have a response to, but maybe somebody else does. Has anyone designed a mixed mode ventilation combining ERVs with operable windows on actuators? I guess where the ERV is tied to a window sensor, maybe?
I have not, but I know somebody who used to work at, everyone's familiar with the Bullet Center, right? It was the Living Building Challenge certified center. And they had windows on actuators. And what they said was you couldn't actually get a nice airtight close on that window with the actuator. So they're having trouble with air leakage for those. So I'm not sure if since then there's better products out, but it does cause some leakage issues. It had caused some leakage issues. Okay.
I've also heard of systems where it's not on an actuator, but where the opposite would occur is when you open the window, if you have a window sensor, then, can shut off your ERV as well. Maybe, that could be an option. Then you wouldn't have those issues with the sealing of the window, potentially. Someone has a question here. Is a wheel or a core more efficient? My MEP is recommending the use of the core because there are fewer moving parts to it. Yeah, there's benefits of either one. I think it also depends on if you're looking at a central system or a unitized system, because typically the unitized do have cores associated with them and there are less moving parts. That is true. A lot of the larger units, some have cores, some have wheels. I have seen better efficiencies with wheels. I don't know if Lois, do you have anything or anybody else on that? But
for the large scale stuff, especially whenever we try to use a fixed plate, we see much lower efficiencies than we would with wheels.
Yeah. Most of the large central system equipment that we utilize does have wheels.
There's an interesting question. Exhaust only ventilation. Does anyone have data on how badly this works? I don't even think you need data. Let's just do a little math. Let's say we're not building to passive house. Let's say we're building to LEED. LEED is 0.3 CFM per square foot of your exterior, right? Or of your building, your six-sided box. So if you're looking at an apartment that has one wall, exterior, and you get 0.3 CFM for that one wall, there's no way you're going to get 100 CFM. If you have 100 CFM in, a kitchen exhaust hood you're turning on and off through that, like 30 wall, there's not 100 CFM there. So the only place you're going to get that air is if you put in a trickle vent that's big enough. It has to be big, which is bigger than what's in the. And you're really just going to pull it from your neighbors. And I think we have done studies on this before because we keep fighting with the hash rate committees who want multiple exhaust only ventilation, and it's just a ridiculous design that has to be put in. Everybody peels off the tree. Doesn't matter. It's nobody cleaning the cores of the individual ERVs. Everybody seals it.
Bertold typed a question here in the chat for me. Why do you use an extra bypass for the ERV? You could just slow down the rotation of the rotary wheel. Actually, we did work with the manufacturer on that, Bertold, and we looked at both options, and it was just within their controls, it was easier for the bypass to be incorporated than the rotary wheel. They kind of went back and forth on both. And it didn't seem to have a huge impact. I think Stephen Winters analyzed both, and it didn't seem to have a huge impact on the sensible reduction either way. It was very similar both ways.
Yeah,
that's just the manufacturer we were working with. There may be another manufacturer that decides, that does it the other way.
Yeah. Okay. We evaluated that for a couple of projects where we are using that methodology. For the manufacturer prefers that, and it's only a few hours a year that it goes down that low where they need to do that. So it's really a very small effect.
So you did not use a bypass?
Correct.
Okay. Oh, so this is if you slow down the wheel, you reduce first the humidity and then only the heat recovery. Yes. Okay.
Yeah. And it's actually Swagon, someone from Swagon, Ashkan from Swagon is posting here that they could do it either way with their equipment.
Yeah. Okay.
Dylan posted a question: where do things typically go wrong with passive house and with ventilation and passive house projects?
In the commissioning.
Nothing need to go wrong if everything is good.
We just had one project where we found that a contractor came in after the fact, just cut a hole right through our ductwork so that they could put a sprinkler line in.
That's not even code compliance.
Commissioning, balancing.
Yeah.
Yeah, you can put anything on paper, I guess, but once you build it, that's when the problems occur.
In my experience, yes, commissioning is a big part of it, especially for projects that are passive house but not certified or close to passive. They oftentimes have the right size of a unit, but they don't go through the full commissioning room by room. And that is some rooms poorly vented and some other overly vented. So that is a typical outcome of poor commissioning or partial commissioning on.
That's a good passive house light, right? We're built standard, but we didn't have all the testing done.
Right. Yeah, and the certification seems just as a cost, but it's really a quality assurance process. So that is, to me, just an excuse not to go through the whole quality assurance process.
Bertold, I think there's a question for you. PHI has a recommendation to increase airflow during summer by 50%. What is the rationale?
Okay, well, it's just as you for cooling you need in summertime, all processes are a little bit more lively, and therefore you need more air. So it's just sticky during summertime. So and the yeah, that's it. Maybe you have some experience with that too. But well,
is that in areas where the cooling is part of the ventilation system?
Yeah, mostly. So if you if you go for passive cooling, it's not. You will not be happy with 150 cubic meter per hour for an apartment. So you need more. And if you just open your windows, you will get 300, 500 cubic meters per hour. Yeah, and this is so. In summertime, there is more ventilation needed. Yeah, more airflow.
So in our climate where we have air conditioning installed, that probably isn't as much of a concern. Because you're never. I mean, maybe in the shoulder seasons you could get some additional cooling by boosting the ventilation, but it's going to be limited because very soon you're going to need air conditioning.
Yeah, that's it. Yeah,
I would say that rule of thumb is applicable in the U.S. in climate zone 4 and 5. In my experience, we had a multi-family project in climate zone 2A, and we really did some polishing on the ventilation rates to keep the ventilation rate as low as possible. in order to avoid bringing in more moisture from the outside. So that is definitely something where we had an ERV for sure. And
that's true. If there's moisture, you should reduce it to reduce the load from outside.
Mm-hmm.
But then you have some more circulation airflow for the cooling, for air conditioning.
Correct.
Yeah, this is
absolutely.
Yeah.
I'm going to read this out loud. I think we can all agree the cost effectiveness of ventilation systems is key to broad adoption of passive house building standards. What have projects worked on how to drive down costs while maintaining quality, and what further opportunities do you see? So, what have we done to drive down costs while maintaining quality?
I mean, from a ventilation standpoint, I think you already touched on it, but just keeping the systems as simple as possible, right? I think that's where that constant volume system falls in. So it may not be the best thing ever, but it's what we can do, within the cost and still maintain a good indoor air quality.
I think one of the opportunities that we see is we need more selection of high efficiency ERVs. We need more competition in the market. We need more options there. We don't have them right now.
Mm-hmm.
Yep. Mm-hmm. And, part of it too is, the ventilation, at least where, in New York City, typically buildings are not designed with ventilation. They're designed with exhaust only, which, as Lois pointed out, doesn't work. So it's an added cost for developers to take on. And so they're looking for savings elsewhere. So, obviously the heating and cooling system is downsized some, which has a minor savings, but I think finding other options for high efficient heating and cooling systems that are cheaper, because, they're also used to installing PTACs, which are very cheap, right? Or window air conditioners, which obviously don't comply with passive house. So finding ways to save money in other aspects then can kind of compensate for that added cost of the ventilation system as well.
Hi, folks. Can you hear me?
Yes.
Yes.
You're back.
Okay. Yes, awkward technology issue. I am on a different computer on a different internet connection, and the browser won't let me to show my video anymore. So.
Okay.
I'm sure I missed some. Thank you. I'm sure I missed some good discussion.
We've been reading the chat and kind of discussing.
Dylan's been feeding us questions in the chat.
Okay, great. Thanks for stepping in there, Dylan. Okay, so I guess we're on to the next question now, are we?
Yeah.
Okay. Okay, I think I can still see them here. Okay, sorry. What was the last question?
It was one of yours that Ken had kind of put out there.
What are the
costs down?
Yeah, how do we keep costs down?
Oh, how do we keep costs down? Okay, great. Okay, so next, another question then is about corridor pressurization. How it's been another issue that's caused problems on passive house projects, and just wondering what your experience has been with that.
With what pressure? Oh, corridor pressure.
Corridor pressurization.
Corridor. That's interesting. Well, we generally have a trash room on every floor, and so we have an exhaust in the trash room, and we balance. We don't let the MEP make more than 2%. Right? They want to pressurize corridor, like you said, Andrew, to keep smell in the apartments, and we just limit the percent that can make that off balance, and we have an exhaust floor.
That's what we typically do too. We pair the trash exhaust with the corridor and have them in balance so that it still pressurizes the corridor. And then you have a very tight seal on your trash door hatch.
The hatch, yeah.
Mm-hmm.
Okay, great. Yeah, so I guess you found ways to work with it. I know it seems like something that's very dependent on the jurisdiction, because other jurisdictions don't allow such solutions for some reason. So it's interesting, yeah, that neither of you have actually had major issues with it, which is good to hear. Now, another question here is, have you seen any solutions from abroad, such as equipment or designs, that would solve one or more of your major problems, but can't be implemented in North America, for instance, for code requirements or product availability or other things like that?
Yeah, I mean, that little project that we all keep talking about, right? That's cooling, heating, and ventilation. That'd be great. When I was in Vienna years ago for the Passive conference, I walked around the floor, the showroom floor with all the products, and I saw 15 different ERV manufacturers, and I kept handing out my copy, and I'm like, why do you guys come to the United States? Why do you come to the United States? And they're like, no way. I don't know how many times we can say it. We need better ERVs.
And maybe Berto, can you maybe share with your experience with the systems in China? Because I know there's been a bunch of development there.
Sorry, I just was with the chat. Could you please repeat?
Sure, just because I know there's been in the Chinese market some good developments in ventilation systems to deal with, I guess, maybe local challenges. I was wondering if you might have any insight to share that could be relevant for North America from that experience.
Well, what I have heard, that some people would like to have these combined systems, what we developed for there, in some apartments in US as well. So, and the Chinese, they do the combined system as they want to operate each apartment individually.
Mm-hmm.
They just want to have an electrical plug and everything connected to the electrical grid and no extra centralized system and so on. So, and this could be, Lois, I very much appreciate what you said about the centralized system. But they say, well, this is not appropriate if you want to sell out all your apartments individually.
Mm-hmm.
And so this is just an extra functionality apart from heating, ventilation, hot water. We just add the cooling and dehumidification, and so you have a full compact unit to do everything. And many people are asking for this. And for example, Stefan Palantzas from Greece, he now imports the machine from Zenda, China, who did this for the first time. Yeah, and so well.
There's a product that just from Italy, I think, that's now being circulated in the US. That's kind of like an ERV combined with a VRF, sort of like a VRF PTEC, but it only has 2 round openings through the wall. I haven't looked at it closely. I just came across it recently. I don't think it's Passive House certified, but something like that could be an option. It's sort of instead of a PTAC, you have these 2 round openings, but the round openings are also serving as your ERV intake and exhaust. So, the penetrations through the facade are not any more than you would have with a unitized ERV system. So it could be, where things are moving. Certainly would save costs for sure.
Yeah, for sure. Especially over VRF. We tested the one that's just heating cooling unit. Not the one that's an ERV as well. We did an air leakage test on it. It's not
You did what? Sorry?
We did an air leakage test on it. We did a mock-up of it.
Yeah.
And we tested the air leakage to see if it would pass Passive air test. And it wasn't terrible. It wasn't, it was like CFM, which is too high to have one in every room, but it's still not out of the realm of possibilities to use in a Passive House project. So once they square away UL and all of that stuff in the United States, I think it's very real option I'd be interested to test the ERP unit.
Okay. Yeah.
Yeah.
Okay, and we have a question from June. If commissioning a system is so important, and it is, how can the average homeowner who wants to get things right go about identifying a top-notch service provider? Any advice from anyone?
Well, we have our certified, trained, testers out there, right? That we should certify testers, right?
Well,
was this maybe a need for some type of resource, or indicate, is that just approaching individual companies for, I guess, the systems they're considering to see who's in their local area that's a trained technician?
Yeah, there's a list of, they're called first raters. They're trained testing that do whole building leakage, and they do testing on mechanical equipment for flow rates and leakage. They also have a rater designation for passive house that learn the PassFast standards and the PassFast, so they have a little more training. So I would say go to the list or the passive house raters list to find a qualified person near you who knows how to test the rate. You want somebody third party outside of HVAC installer. You don't want your HVAC installer to tell you that this.
Yeah.
Okay, great. Next one here is from Sarah. More of a general question. Are there significant studies that show how poor exhaust-only ventilation works with trickle vents to really provide fresh air, for instance, measuring CO2? So I think that's maybe to contrast, we're confident passive ventilation works. Is there contrasting evidence showing poor exhaust-only ventilation is poor?
I think we talked about this one already, Andrew. I think this one.
Oh, did we?
Their chat, yeah.
Oh, okay. Sorry, missed that then. Next one here is from John. What is the origin of a relationship between low, medium, and boost rates? 54%, 77%, 100%. Bertold, I think this one's for you.
Well, I just try to write it down. It's a rough estimate. Do it 30%. Start from an average level, what you normally use, and then 30% up and 30% down. And but please don't take these numbers not too strict. And in the end, the user they will choose the level individually here and there. So it's a guess to do it. And well. Or Andrew, what is your experience?
Yeah, I think we sometimes not interpret it liberally, but for instance, Lois has already spoken about the difference between passive house rates and code rates, multifamily, where they can be substantially higher. One of the strategies to kind of balance the two requirements is to design and commission the system at the high rate, but also have it operate and ideally commission at the passive house rates. And that difference is often more than 30%. So we say, okay, well, that boost rate for ASHRAE requirements is more than 30%, but that's fine. I mean, it kind of meets both purposes, right?
Well, but this is another discussion. So if your ASHRAE or other requirements are much too high, you have to argue and see that the user afterwards can come for a reasonable airflow level. Yeah. So, and then you may have a little different numbers. So, but these numbers, what we recommended is just have a normal level and have something up and something down.
Good, Andrew.
Okay.
We're
great. Yes.
We're at
time. Okay.
So I know we could keep going all evening, and I think it's like almost midnight. Bertold, where you are?
No, 11. Well, almost. Yes, 11:30. 11:30. Well. So it's night. You see in the background.
Yeah. So I'd like to wrap up, if that's okay, and thank all of the presenters here in session 2, as well as, again, the presenters in session 1, speakers, and the audience. A lot of great questions and good discussions. And I think, like any good discussion, it's raising more questions and certain things. You know, there are many topics we weren't able to even really touch here today because we knew that there was just too much to cover. And we'll be looking forward to doing it again and digging in different directions in different ways, perhaps. So thank you, everyone. And we wish everyone a good night. And we look forward to being in touch. So thank you all.
Thank you,
Have a
everybody.
good night.
Thank you, everyone.
Thank you. Bye-bye.